let's start, everyone. First of all, I welcome you all on behalf of Team Game Club India. So basically, we are a consultancy firm which provides the students technical skills and practical exposure through our knowledge and chemical engineering softwares. Please mute yourself, everyone. Okay. So we are helping students to get internships, jobs, and develop skills that upscales their practical and professional career. And we at Game Club India offering different courses regarding process engineering that includes Aspen Plus, Aspen HYSYS, Aspen EDR, that is Exchanger Design and Rating, and also Process Design Engineering, which is detailed course for a process engineer, and Distillation Column Designing and Troubleshooting, and also PSV sizing. Okay, so again, we what are the features of our course? We provide live sessions plus recorded. Yeah, just a minute, let me check. It is visible. Is it for all of you?
No,
Yes,
ma'am, no.
ma'am.
Yes, not visible.
Your screen is not shared actually, I think.
Yeah.
I have shared, just a minute. Now is it visible?
Yes.
Yes, ma'am.
Yes.
Yeah, okay. So we provide live sessions plus recorded lectures. I mean, if you need any recorded session for your doubt clearing, so you can refer them. And also we provide doubt sessions plus practice on our Aspen Plus HYSYS software. So after the course completion also, if you need any assistance from our tutor, we can provide you. And also after the course completion for Aspen Plus and HYSYS, we provide guidance for Aspen user certification. Okay. So today's session is included in process design engineering course, which whose duration is 50 hours, and we always schedule the classes in the evening, so it will be feasible to all of you guys. So I hope you will enjoy this session, today's session, and I hope this will be helpful for your career growth plus knowledge. And thank you. It is from my side, and over to you, sir. Hello.
Yes, thank you.
Thank you, sir.
Okay, so thank you for the introduction. So once again, welcome everyone to Camp Club, right? So my screen is visible and I am properly audible, right?
Yes, yes,
Yes.
yes,
Okay.
yes,
Yes, sir.
Okay, so before starting the session, just some quick.
Screen is not visible, sir.
I think it's visible because it's showing me I'm sharing. So okay, you can just rejoin if it is not. Okay, so just some quick. Yes. So some quick instructions. So I request everyone to be attentive. You can ask all your doubts, right? You can interrupt me. I will answer all your queries. And I request everyone to kindly mute yourself and do not create any uh, disturbance. So it like we can complete the schedule on like the topic on time. Okay. So without wasting time, let us start. So basically, when we talk about the reactor, right, or the agitator, right? So these are the two things which are the you can say the heart of any chemical plant, right, or any process, right? So basically, the part in which the reaction happens, right? the vessel or the equipment which helps to get the reaction done is basically called a reactor. And one of the equipment which helps in proper mixing, proper stirring, or the agitation, right, which basically enhances the rate of reaction, you can say, or the time required for the reaction, right, that is nothing but called an agitator, right. So basically how important it is to design a reactor in a proper way and the agitator, so that you get the desired conversion or the desired yield, and you are running as per the basically you can run your plant at commercial level and match the results with respect to a lab scale plant also, right. So the most important thing is to scale up an agitator from laboratory scale to the commercial scale, right. Okay. So the outline of the presentation is the introduction, the definition, then we will see the different types of reactors, different types of agitators, what is vortex formation, what is baffling, what is the power requirement for the agitators, shaft design, hub and key design, and scale up of the agitators. Okay, so this is nothing but an reactor where your reaction is taking place. This is the motor, right, which is basically connected through a coupling assembly to the shaft of the agitator, and this is nothing but the agitator which helps in mixing and proper agitation, right. So what are the different types of agitators available in industries, right? So it's a normal kettle type reactor, so it is nothing but a batch reactor. Autoclave is there, so which is basically a high pressure reactor specially used for hydrogenation, right? So autoclaves operate at high temperature, high pressure as high as 100 atmospheric pressure, right? Bubble column is there, right? So bubble column is nothing but a reactor where your liquid is filled inside the reactor and you are passing the gas from the bottom, and whatever the reaction happens, right, the liquid will be under circulation, right. So whenever your reaction takes place, you can replace that fluid. Similarly, we have gas parched reactor. So it is nothing but a stirred tank reactor with gas which is parched inside the reactor through the agitator. Next one is fluidized bed reactor, right? So that is basically where your kettle is bed, right? It's which is in form of a powder. It's getting fluidized, and your gases, basically this is used where your gases are cracked. So basically in a fluidized catalytic cracker where we are cracking the long chain molecules, hydrocarbons, into short chain hydrocarbons and hydrogen, we are getting C1, C2, C3 cut, C4 cut, right? So basically when we are uh, generating the small chain or short chain molecules, and basically LPG, it is butane C4 from the long chain molecules and hydrocarbons, right. Next one is the extrusion press or a screw conveyor. So basically when you want to react, right, two different solids, right, or you can say a paste. So basically दो अलग अलग semi solid या semi liquid paste को आपको reaction करना है, right. So in that case you can use a screw conveyor or extrusion press. Then we have and film is created inside the tube, which basically leads to reaction. Then there is photochemical reactor where photochemistry comes into picture, right? Spray column, again it's a normal absorber column, right? Then air life reactor, slurry reactor where slurry is already filled inside and you are sparging the gas, right? Trickle bed reactor when here your liquid as well as your gas both are passed through a trickle bed from top, and at the end your reaction mass, converted mass, will be collected, right. Next one is bioreactor. So basically you can see this type of reactors in fermentation and alcohol industry. Sonochemical reactor where the acoustic property, right, where you are using the high frequency sound waves to vibrate, or you can say to agitate the reaction mass, right? So what are the different requirements for reactor design? What do we need as a data? What do you need to design a reactor? Basically, you need stoichiometry, you need feasibility of the chemical reaction. So up to what extent your chemical reaction will take place, right? What is the nature of reaction? Is it fast? It is slow, right? What is the exothermicity? What is the endothermicity of the reaction, right? So is it exothermic or endothermic, right? If it is any of the case, so what should be the jacket design, right? What is the equilibrium constant? What is the rate of reaction, order of reaction, right? What are the properties, the physical and the chemical properties of the reactants, right? Is it foaming? Is it hazardous? Is it corrosive? Next one is, what is the reaction mechanism? How the reaction is taking place, right? Is it polymerization? Is it chain reaction, right? So what type of mechanism the reaction is following, right? What is the mode of operation? So basically, this is the most important thing, whether it is a continuous reactor or a batch reactor. Even you can convert a normal batch process into continuous process, but that's where the real engineering comes into a picture, right? That we will discuss. What is the mode of heat transfer? So basically, most of the cases it is always convective, right? So how to design the jacket or the coils, right? So you can like achieve the desired heating time or cooling time, right? That also we will see. What are the different types of agitators? What are the different levels of mixing, or you can say the scale of mixing? So the mixing should be slow, it should be normal or regular, or it should be very high vigorous mixing, right? So that we will see. So mostly when you see, like whenever you are sparging the gas, when hydrogenation is done, so there your mixing scale is, level of mixing is very high, right? Your agitator is rotating at good amount of speed. But when it comes to crystallizers, right, where we are using the anchors, then the speed is minimum, right? The rotations are very slow, just because at higher rotations your crystal might break, right? So what should be the level of agitation, so that your desired basically whatever you are desiring, right, the conversion or the reaction, whatever it is achieved. So that is nothing but optimum selection of a agitator level of mixing, and this is basically done based on RTD study. So that is residence time distribution, right? Mostly RTD will be applicable for a continuous reactors, so that is continuous stirred tank reactor, CSTR, and plug flow reactor. However, for batch reactor, RTD is not that much important, right? Then selection of material of construction. So based on the properties of the reactants or the product that will be forming, you have to select the suitable material of construction. Installation of the reactor, safety and control aspects related to operation. So what type of control from safety point of view you will be giving, right? And the last one is the cost, the most important one, again the cost. So these are the factors which will come into picture whenever you are selecting a reactor, right? So let us quickly see what are the different types of reactors, right? So first one is a batch reactor. So you can see here the gas is sparged. There is in bottom there is a sparger, there is an agitator. So this is a very simple batch reactor. So this one is the loop reactor, right? So loop reactor is like, it can be converted as a continuous reactor also. So
Sir, you have muted yourself, I guess.
like, I think someone has muted me. Okay, okay. So just like a batch reactor, here in loop reactor also, where this type of configuration is very, very common with hydrogenators. So what you can do is, just like this batch reactor, you will be sparging the gas in the bottom, right? So you can feed the reactants, you can sparge the hydrogen gas and continuously keep those reactants, or you can say your unconverted product, or you can say your crude mass into circulation. You can withdraw one steam, राइट? सो यहाँ से आप एक स्ट्रीम विड्रॉ कर लीजिए, पुट अ डेंसिटी मीटर, और यू कैन से basically densitymeter is a good estimation. So जैसे ही आपका conversion होता है, suppose after hydrogenation there is some raw material, and after getting hydrogenation its density will change, or its any one of the property will change, right? So what you can do is, as soon as the reaction gets completed or your required density is achieved, you can start withdrawing the stream, right? So you can use this type of loop reactor for continuous operation also, right? Similarly, we have a tubular reactor, so mostly in fired heaters, right, where we are doing the thermal cracking, basically in refineries where there are fired heaters. So basically we crack the heavy residue of the crude in this type of tubes, and at higher velocity, the fired heaters, the cracking happens and it exits at good amount of temperature, somewhere around 500 degrees centigrade, and it gets its resident time in the delayed coke drum, right, in the coke drum. So this type of reactors, tube reactors, so these are nothing but one type of plug flow reactor, right? So this type of tubular reactor are also common with the, you can say, the manufacturing process, right, by the Haber's process. Again we have a series of stirred tank reactor, right? So reactor number 1, reactor number 2, reactor number 3. So based on the conversion, right, your material from the first reactor will be transferred to the second, and from second to the third, right? So there might be a case where, suppose you want to achieve the 99% conversion. So initially 0 to 50% conversion has to be done at low level of agitation, right? Slow agitation. Then 50 to 80 has to be done at medium level of agitation or medium scale of agitation, and at last you have to do the vigorous agitation, right? There can be a case. So in that particular case, you can use three different CSTRs, or you can say three different STRs in series based on the scale of agitation. The case might also be reverse also, कि starting में आपको agitation ज्यादा करना पड़ेगा, जैसे जैसे आपका प्रोडक्ट का कन्वर्जन होता जा रहा है, राइट, यू आर मेकिंग सम क्रिस्टल्स या सॉलिड्स कुछ बन रहे हैं एज अ प्रोडक्ट, so you have to reduce the scale of agitation, otherwise your product particle size will get damaged. So to achieve the required PSD, that is a particle size distribution, you have to control your agitation, right? Next one is the heterogeneous continuous reactor, right, where there is a heating or the cooling coil. The catalyst solution is filled inside the reactor and you are passing the reactant gases from the bottom, right? Similarly, you can have a fixed bed catalytic reactor where there is a bed of
Sir, I
catalyst.
think you forget to change the slide, sir.
Sorry.
No, sir, now it is visible.
Okay. So we have a which is fixed, right? So basically it can be a wire gauze or it can be some molecular sieves of the catalyst, which is fixed bed, and you are passing the gases. So once these gases pass through the catalyst bed, they get reacted and get converted. So mostly wherever you are finding the gaseous products, right, just like ammonia is there, right, or ethylene oxide is there, or you can say like wherever you are finding some reformer is there, so in those cases you will always find the fixed bed reactors. So mostly you can find the plug flow reactors, right? This is a one type of plug flow reactor only. So plug flow reactor, continuous reactor, you will find only and only with the gaseous products, right? It's really difficult to operate a continuous reactor with the liquid products, right? Next one is the baffle tank reactor, where you are feeding from one end. So it is similar to a heat exchanger, you can say. There might be tubes inside for cooling or heating purpose, and the baffles are providing good amount of agitation, right? So this is also one of the case. So it's rare. I haven't seen this like reaction.
Sir, can you please explain how a packed bed reactor represents PFR?
So basically, a packed bed reactor, exactly, it's not a PFR, you can say. Actually, the ideal case is basically this tubular reactor. So packed bed is basically a combination of PFR and CSTR, you can say. Like it's dispersing the flow, right? So you cannot say it's not an ideally a packed bed reactor, but definitely there are some you can say like the bed is there, right? So whenever the gas is passing through that bed, so the plug flow, you cannot achieve the exact plug flow in the pack bed. Definitely उधर आपका पूरा dispersion हो जाएगा. So but its operation is similar to a plug flow reactor, you can say, with some deviation. right?
Okay. Thank you, sir.
Next one is the fluidized catalytic cracker. So again, this one is one of the most common reactor in the refineries where we produce the LPG, right? So here there is this one is a reactor and this one is a regenerator, right? So you are feeding from the bottom, you are again carrying this catalyst as well as the compressed air, getting your bed fluidized, right? And the products will be cracked products, right? You are doing the cracking, right? So lighter products will be received from the top, whereas a slurry of the catalyst as well as our unreacted products or whatever the impurities are formed will be going to regenerator, where you will do all the burning and you will burn out the fly ash. जो भी आपका ash और your impurities are there, basically आपका cracking होने पे क्या होता है, heavy molecules का cracking होने पे coke dust is generated. So we'll burn all those coke dust or your fines and you will regenerate the catalyst which will be again reused, right? Similarly, you can have a jet reactor where you can use a ejector to basically suck the basically this you can say the gas, right? So here you can see this particular case gas is this is the inlet of the gas, and because of the you are continuously circulating the liquid through this ejector. So because of the vacuum generated due to this ejector, your gas will be sucked in. Along with that, a fixed amount of catalyst is being continuously fed, and this is called a jet reactor, right? Again, these type of reactors. Yes.
Sir, in fixed flow fused bed reactor, we are mixing the catalyst and reactant, sir.
Which one?
In fixed fuelized bed reactor.
Yes. So we are mixing the catalyst, the reactant, and compressed air for fluidization.
Okay, sir.
Next one is again the loop reactor that we already discussed. So different types of loop reactor. So in one of these, there is a bed of yes.
Excuse me, sir. I have. Can
Yes.
we use the jet reactor? Hello.
हाँ बोलिए.
Can we use a jet reactor for a high vacuum system in industry? Because jet reactor you can use for a vacuum is generated, so we can say ejector is used for high vacuum, and we are providing high vacuum in reactor. So can we use jet reactor for high vacuum requirement?
So basically here the reaction is not carried out in vacuum. So here what is happening? See, you want to maintain some liquid to gas ratio, correct? आपको कुछ liquid to gas ratio you want to maintain. So in this case, suppose आपका liquid का pump, suppose there is no ejector system. Suppose you are mixing the gas and liquid with some ratio controller or any other medium, right? So in case आपका pump अगर trip होगा यार, you will get some faulty flow. आपको flow rate सही नहीं मिल रहा है. So in that case, gas will continuously pass. So in order where your gas to liquid ratio is critical and you want to you don't want to deviate from that, so in that case आप क्या करेंगे, गैस का इनलेट आप इजेक्टर के पास दे देंगे. तो जब आपका लिक्विड का फ्लो रेट बढ़ेगा, your vacuum will be higher. In that case, your gas will also be higher. So by controlling the liquid flow rate, you are ultimately controlling the gas by controlling the vacuum. Is it clear? आपका रिएक्टर में वैक्यूम नहीं होगा डेफिनेटली.
ओके ओके.
आपका इजेक्टर क्या कर रहा है, गैस साइड से गैस को सक कर रहा है. क्लियर है? वो गैस को आप सक करेंगे, यू आर बेसिकली इंड्यूसिंग द गैस टू रिएक्ट विद द लिक्विड, राइट? सो आपका सक्शन, गैस का सक्शन और पैरेलली लिक्विड का हाई वेलोसिटी, राइट? So basically that will create some turbulence and mixing so that your liquid and gas reaction will happen in place of in presence of catalyst. Is it clear?
Okay.
So next one is again the monolith reactor where there is a basket filled with the catalyst, right? So where you are inducing the gas through the turbine, this impeller, right? Similarly, this is a CSTR where you are continuously circulating, and one of the stream will be you can say this is a reactor, this is a fresh hydrogen, and one of the stream, this one is the you can say the withdrawal stream. You will continuously withdraw the stream based on the conversion, right? So this is one example of the CSTR where there is a catalyst inside, and this is the continuous charging of the catalyst. Again, here you are feeding the hydrogen, right, based on the vacuum that is generated by this ejector and flow rate of the liquid. So that will pass through this bed of catalyst and go inside the reactor, right? So these are the different configurations of reactors in industries, right? So however, it takes like a good amount of time basically to understand the reaction chemistry, to get the equilibrium constants, rate of reactions, to know the order of reactions, and then you can do the sizing. So mostly when we talk about the PFR, so there the residence time distribution or flow chemistry takes in like comes into picture, which is like very time taking to understand and to you can say scale up at commercial scale, right? So most of the time we are always going with the batch reactor, right? Suppose giving a very simple example, right? Suppose you have a benzene ring you have, right? So benzene को आपको कोई भी आपको unit process करना है. So suppose you want to do chlorination of benzene, right? So most of the time we do it in a batch reactor only, right? We are sparging the chlorine in the bottom of the reactor, continuously circulating it, and once the reaction is happening, we are continuously withdrawing the mass out, right? So that cannot be done in a PFR, because to make that particular reaction continuous in a plug flow reactor is very difficult, right? So उस केस में आप क्या कर सकते हो, बेंजीन को सपोज आई कैन वेपराइज at high temperature, I will convert benzene into vapor, and similarly chlorine also in vapor. I will feed in a tubular reactor, right? And at the end of the reactor, my benzene will get reacted with the chlorine, and my desired product I will condense that and distill out, right? So it's easier at when you do this analysis, but it is very difficult to scale up, because little bit of deviation from the operating parameters will lead into upset. So most of the time it is always preferred to go for a batch reactor, right? So when we talk about the continuous reactor, then only gas phase reactions are only suitable. So जो normal temperature में हो सकती है, या फिर जैसे कि हेबर्स प्रोसेस है जहाँ पे अमोनिया और हाइड्रोजन का आपको अमोनिया बनाना है हाइड्रोजन एंड नाइट्रोजन से. So you cannot do that reaction in a batch reactor. आप हाइड्रोजन लिक्विड नाइट्रोजन को आप मिक्स नहीं कर सकते हो, स्टर नहीं कर सकते हो. So PFR will only come into picture for the gases which are normally not condensable at atmospheric pressure, and which cannot take place in a stirred tank reactor, right? Or you can use a PFR where your production capacity is extremely high, right? So that in that case only it will be beneficial, right? So these are the differential equations. So basically used for the design, right? So just we will just go through it. However, our discussion will be based on the batch reactor only, right? So this one is a differential form. So you can see here the concentration changes with time, but it is uniform within the reactor, right? So with respect to टाइम आपने इनिशियली टाइम t is equal to 0 पे रिएक्टेंट डाला है, right? You are feeding the another limiting reactant. So at time t is equal to 0, your conversion will be 0. As the time progresses, your reaction will happen. So if it is a good agitated reactor, अगर आपका mixing proper है in a batch reactor, so with time your concentration will change, but your concentration will be uniform inside the reactor. So that you can see, right? So you can see here dx by dt is there. So concentration is changing with respect to time, right? Here your conversion is changing, right? Your product is getting converted, but it is uniform inside the reactor. So that's why this is a batch reactor form, right? Similarly, when we talk about the CSTR, right? So this is the equation: V by Fa0 is equal to X upon minus R, where X is the conversion, Fa0 is your molar flow rate, V is the volume of the reactor, minus R is the rate of reaction, right? So here you can see the equation says that concentration inside the reactor is uniform, right? So you can see here Ra, there is no differential or integral term. So concentration is here the X is constant, right? The rate of reaction is also constant. There is no integral or differential term. So concentration inside the reactor is uniform, and the exit concentration is equal to concentration inside the reactor, right? So continuously your raw material is coming and continuously your product is getting out, right? So here the concentration inside the reactor is same as that of concentrate, which is reactant or the product that is exiting the reactor. Similarly, for the plug flow reactor, what happens here? The concentration with respect to the length of the reactor. Initially आपका concentration कम है, but with the time your concentration will change, right? So concentration and reaction rate varies with respect to the length or the geometry of the reactor, right? So you can see here minus xa as well as minus ra, both are inside the integral term, right? So these are the equations basically governing the operation, or you can say the working, or the you can say engineering behind these three types of reactor, right? So what are the industrial? Yes,
Hello.
yes, Bully.
Hello, sir. I will decide. Sir, as we have seen the performance equation for ideal system right now. So in this equation, we have a minus RA entity. So just want to know, as we know that minus RA equals to rate constant multiplied by concentration raised to number of orders. So is there any method to calculate the rate constant right now?
So basically what happens if you want to like calculate the RA, right? Rate of reaction comes from some equation, right? So rate of reaction is basically minus RA is equal to K into dc by dt, rate of concentration with respect to time and some constant K, right? So what you can do if you want to calculate the rate of reaction in laboratory, right? So what you can do is you can at time t is equal to 0 note down what was the concentration of the you are continuously feeding the reactant at time t is equal to 0, your concentration of, yes,
नहीं नहीं रुक 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 पहले ये डाल
mute
ये भूल
yourself.
गया टमाटर डालने का
Okay, so at time t is equal to 0, you know the concentration of your reactant is Ca0, concentration at time t is equal to 0. Now with respect to time, as you are proceeding, your concentration of the reactant will slowly reduce and your product concentration will increase. So you can plot the chart of concentration with respect to time. So what you will get dCA by dt, right? So minus Ra, that is basically the rate of reaction, is proportional to K into dCA by dt. So what is the order of reaction you will get from the nature of the curve? Like once you know the nature of the curve, whether it is first order or the second order or third order, mostly the reactions are first or second order or zero order, right? If it is linear, then you can get like from the, you have the equations, right? Rate reactions ki aapke paas equation hai for the first, second, third. So from the intercept or from the slope, you can find out the K values. So once you know these K values, equilibrium constant aapke paas hai, you can find the rate of reaction. So rate of reaction is given like is equal to some value multiplied by the rate of change in concentration. Is it clear?
So sir, the K value we can only obtain through experiment. Is there any
Yes, definitely. No other thing
database?
experiment के बिना आपको नहीं मिल सकता है. It's not possible. You definitely have to conduct the experiment, and that to multiple times. Then only you can intercept. अगर एक बार आपने experiment किया, right? So mostly when we scale up the reactor, जब आप PFR जैसे कि gas phase reactions को scale up करते हैं, it takes nearly 1 से 2 साल लगता है, because आपको 33 डिग्री पे वो कर्व्स अलग मिलेंगे, 35 पे अलग मिल सकते हैं, 40 पे अलग मिल सकते हैं, right? With the raw material quality it will change, with the geometry of the reactor it will change, with the type of agitation it will change, with temperature it will change, with pressure it will change. So you have to optimize कि कौन से temperature पे you are getting the desired conversion with minimum time. Is it clear?
So sir, actually what happened right now is we have a reaction which is having a maximum conversion rate, and the parameters has already been fixed right now. But in past, no one has even calculated this rate constant. So as the parameter is fixed and the conversion rate is high, we can go for one or two reactions to get that K value right now.
See, basically K values you will get from the experiment, right? So like आपका like what is the question? Basically if you are doing the scale up, right? So अगर आपके पास unknown product है, unknown chemistry है, like then only you will go with this type of, like otherwise mostly when as far as my experience is concerned, so mostly it like suits ideally at like very large scale. अगर कुछ ऐसा critical है, then we perform this type of study. Otherwise mostly we don't do this type of study for the basically designing of the reactor. So what we do is जो भी raw material का जो volume है, that volume we take as the operating volume, usme 30-40% margin we take. So that is the practice in industry, because we do not have that much time, right, to scale up. So this will be only and only applicable where there is a plug flow reactor, जहाँ पे आपको continuous plant design करना है, और even a smallest mistake can result into huge amount of losses. But that is not the case with batch reactor. Batch reactor is nothing but a mixing tank only, right? So in that case, these equations, they are like does not play as significant role as that of PFR or CSTR.
But sir, if we want to calculate the conversion rate, then we have to go through this
Definitely.
all the steps.
Yes, then you, like, if you want to calculate the conversion rate, then you have to go through this rate equations, right? So that you need to do. Otherwise, आप theoretical conversion तो normally भी निकाल सकते हो if it is a batch reactor, but for continuous or for PFR, you have to follow the rate equations.
Sir, one last question. What if we go to the equation like RNS equation? Because from that source also we can calculate the K value, but we require that
Definitely,
activation energy.
you can go from the RNS equation से आपको equilibrium constants मिलेंगे, but like as far as my experience is concerned, even we find difficulty in getting the CP values also, right? So basically chemistry में कैसा है कि unknown जहाँ पे रहता है, where raw materials are exotic, your products are exotic, right? आपको एकदम अलग complex chain molecules बन रहे हैं. So even if you go through that method, you will not get the accurate answer, right? So K values for certain desired reactions, right, जिसका कुछ patents है या जिन्होंने उसका R&D किया है, so in that case we have some K values with respect to some temperature, pressure. Otherwise, to generate the new K values, right, with respect to the theory, it's very difficult to generate, right? So mostly this type of work is done by the PhD people at the lab scale, right? So again, scale up on that basis. Yes.
So at present, if we don't have any time, that if we don't have that much time, then we can go through those literatures which had been done in the past by the PhD scholars, and
Correct.
we can take it as a reference. We can take a value as a reference for zero order. This much is the value for first order. This much is the value.
No,
and so
I'm
on,
not saying
right?
some another basically some other reactions, but basically there are some like few process only whose K values are very known. Otherwise, आपको नए कोई reaction का आपको, like suppose you have to synthesize a new product, right? और उसका मुझे आज ही सारे K values, so it will take time and it requires reliable equipments basically, right? आपको जो भी study करने के लिए, right? So that then only you will be able to know the K values. So just like आपको CP value है, जैसे कि specific heat है, so I know the specific heat of water, methanol, ethanol, benzene, toluene, everything. But if there is a complex molecule, so उसका specific heat मुझे नहीं मालूम होगा, right? Because उसमें multiple benzene rings है, multiple groups है. So in that case, what we do, we have some equipments. तो जहाँ पे उसको हम रखेंगे, उसका टेम्परेचर बढ़ाएंगे, we'll see how it is behaving, और उधर से कुछ CP value derive होगा. So these type of equipments are also there, right? Which like wherever you start doing the reaction, it will monitor the rate of reaction with respect to time. The machine will generate the plot, right? So that is there, but this type of basically advanced studies done at R&D level. So mostly it is not used at commercial level during the plant design.
Thank you, sir.
Okay. So we'll see what are the industrial examples of plug flow reactors. So it is a conversion of ethylene to polyethylene, right? Hydrolysis of ethylene oxide to ethylene glycol, right? Similarly, fixed bed catalytic reactors, right? It is again Haber's process to manufacture ammonia, right? Methanol synthesis from carbon dioxide, carbon monoxide, and hydrogen, steam reforming. Again, in the manufacturing of sulfuric acid, we have this contact process, right? So conversion of SO2 to SO3 in V2O5, vanadium pentoxide catalyst bed. So these are the common examples of plug flow reactors, right? Similarly, what are the examples of CSTRs or mixed flow reactor? So it is nothing but carbonylation of methanol, gives acetic acid, right? Similarly, oxidation of acetaldehyde to give acetic acid. So mostly you can go with the plug flow reactor, or your your plant will be running 24/7 365 days, where your production capacity is very high, your market requirement is very high, right? So in that case, your engineering is worth. आप जो भी time invest कर रहे हो, right, whatever time you are spending, you are doing the entire engineering, you are having like your continuous plant capex is somewhere around 5-6 thousand crores, right? Then it is worth, because the capacities are massive. But जहाँ पे आपको कुछ भी लोकल प्रोडक्ट है, और उसको कुछ यू हैव सम सीजनल मार्केट, राइट, 1-2 साल का रिक्वायरमेंट, सो इन दैट केस यू कैन नॉट गो विद द basically the continuous reactor, right? So the type of the reactor again depends on the quantities, depends on the market, right? What is the production quantity you want to produce, right? So based on that you will select the reactor type. So why should we go for mixing? So when we talk about the agitated tank, right, mostly we'll discuss about the design of the agitator, right? So why should we go for the mixing? So it's the heart of the chemical industry. Basically, you should have the uniformity of the composition inside the reactor. You should have a desired flow pattern, right, to control the quality of the product, to maintain the heat transfer at higher possible rate. So as your heat transfer will be at highest possible rate, your time of production, or you can say your cycle time or your batch time, will be minimum. And to separate two phase mixtures effectively. So these are the different purpose of mixing. So what is the difference between agitation and mixing, right? So Maccabee and Smith, right? So what he has said is, many processing operations depend for their success on effective agitation and mixing of fluids, right? So what is an agitation and mixing? So mixing is a random distribution, right? Mixing does not have any engineered pattern, right? So mixing, आप जब normally घर पे आप, when you dissolve the salt, right, in water, what do you say? You always say, I have mixed the salt in water, because there is no desired pattern, flow pattern नहीं है उसमें कुछ, there is no proper engineering. So that's why it is called mixing. But when we talk about the reactor, it is always called a agitator. घर पे जो हम चटनी बनाते हैं उसको हम मिक्सर बोलेंगे, because it is random distribution, right? So basically we should always focus on agitation, right? So it is an induced motion of a material, right? So we want our material inside the reactor to flow in a particular flow pattern, right? So pattern, अलग अलग pattern हो सकती है. It can be radial mixing, axial mixing, tangential mixing. So it takes place inside the reactor. So what is the purpose of agitation? So basically it can be suspending the solid inside the reactor, so that is a catalyst particle, right? Blending immiscible liquids, right? Dispersing the gas, जहाँ पे आपको gas liquid phase reaction है, so you want to disperse the gas uniformly in the reactor. You want to increase your heat transfer between the liquids and the jacket. So in that case your agitation is very crucial.
Sir,
So
hello.
yes.
Sir, I have one doubt. Can you repeat? Can you go back to the previous slide?
Yes. This one?
No, sir. Previous one again. Sir. Again, previous one. Sir. Actually, here it is mentioned to separate the two-phase mixture effectively. Last point it is. How I am not
Yes.
getting that point. To separate two-phase mixture effectively means I am not getting that point. Actually.
Basically to separate
Can
two
you
phase
explain?
basically I need to like see basically what it means to say.
Okay.
I will just confirm you, like I think by mistake it has
Okay.
come, or I will confirm on this.
Okay.
Okay.
Okay. Nice. Continue.
Okay. So where it is required, so basically blending of miscible liquids, right? So I think it is actually to separate नहीं होगा, either to mix two phase mixtures effectively, right? Rather than separating, it is basically mixing, because here also it is we have mentioned,
Yes,
right?
exactly.
Here you have mentioned the blending the miscible liquids, as well as here we have mentioned blending of miscible liquids, or right. So wherever we want blending of the liquids, like liquid mixing, or solid suspension, right, gas absorption is there, dispersion. For the different types of purpose, we have different types of agitators, right? So these are the common applications. So a good
Sir,
mixture should
sorry for interruption. Maybe some of the in some of the distillation, batch distillation, the purpose of agitation is to getting better heat transfer at
correct.
good rate. So maybe that scenario considered for the particular statement.
Which one? This one?
No, just previous. Yes, yes.
Maybe.
To separate two-phased mixture effectively.
Yes,
Maybe.
maybe.
So basically like ऐसा हो सकता है, like where there are two different phases, and जहाँ पे आप like there is some gas which is dissolved inside a liquid. So if you agitate and heat it, so might be gases might
I think this is regarding extraction, sir, to maintain certain mixing your RPM to separate out two phases.
yes, that can be
Also,
also one of,
in,
because
in case of clarifier, sir, in case of clarifier, we separate mixture on basis of density, density difference.
yes,
So in
that
that
can
case,
be
we
also one of
provide,
the,
yes.
yes, that can also
Yeah.
be one of
Yeah.
the criteria.
Actually, in the industry, whenever you do the workup, when organic and aqueous layer are there and some salt are dissolved, for that separation it is used.
Yeah, so there are different applications. So basically here, like for the organic and aqueous separation, you will not go for mixing, you will go for settling, right? So here I think separation of,
Not like that. No, not like that. Sometimes impurities are there, and we have to mix and
No, sir, it
wash
is
the
like
impurities.
extraction, we can say. Extraction it is.
Yeah, extraction,
yes,
workup, it is called in the industry.
yeah.
Is a solubility difference.
Yes, that we can do basically
Yes.
extraction. Suppose like the in the aqueous layer, if some of your organic material is dissolved, right, some solubility, so you can add some organic solvent, right, so to extract that material from the aqueous layer, and that mixing, that is okay. So for extraction process, then in that case, it is, this statement is correct, right?
What happens most of the time, the main product contains the impurities, which are
Yes,
washable by water. So that
yeah,
time water is used to organic layer and dispersion made. So the
yeah,
impurity get dissolved in the aqueous layer, and the layers
correct.
are separate, just like that.
Yes, correct. So basically, when we wash out this product layer, na, so in that case,
Yes,
along with water, some of the organic contents get slipped away. So we can use some organic solvent to recover that or extract the product that has slipped in the aqueous layer, right?
both way, right.
Yes.
Sir, normally during the mechanical agitator contractor we can say MAC. So there the dispersion phase and continuous phase happens. During that scenario, these two phases, that organic phase and aqueous phase, can be separated out from middle of the mechanical agitator contractor. On bottom side, we can say organic phase we can separate. So there will be a density meter also installed in the pipeline to make sure that our product is properly mixed and separating in a proper compositions. So that is also one of the reason where two phases can separate out through the mechanical agent contractor. So that is right statement actually.
Correct. Yes. Okay. So just any doubts, anyone in between, you can ask. So if till now, if you have any questions, you can ask, right? Any questions, anyone? I hope
No,
it
sir,
is
no,
clear,
we
right?
can proceed.
Okay, yeah. So basically a good mixing, so what is the basically desired from a good mixing is you should consume the minimum power, right? It should efficiently mix the desired reactants in optimum time. It should give you the best possible economy, right? The maintenance should also be minimum. It should be durable and trouble free operation. So basically your breakdown should be minimal. It should be a compact, right? So you should not be consuming much good amount of space. So आपको compactness में, like with minimum volume, how you can handle the best possible mixing, right? So that is a criteria of good mixing. So what are the considerations for designing? So what is the amount of energy required or the power required, right? Process has to be well defined, right? Properties of the components to be mixed that you should know, details of the tank geometry, outline of the mixing cycle, right? So basically what is the, like how mixing has to be started, how it has to end, right? What should be the optimum rpm, right? What should be the type of agitator? So these are the important consideration in design of an agitator. So what are the different factors, right? So the type of vessel. So basically you can say type of vessel, it means whether is a horizontal or a vertical, right? What is geometry, what is the L by D ratio, right? What is the circulation pattern, what is the location of the agitator, whether it is a centered agitator, whether it is a offset agitator, whether the agitator is located in the bottom or it is a top mounted, what is the size and shape of the vessel, what is the diameter and width of the agitator, what is the method of baffling, right? So whether there are some basically dip pipes are there or baffles are there, angular baffles are there, right? What is the power requirement, what is the shaft overhang, what is the type of stuffing box or seals or bearings, right? So these are the different factors which will decide the agitator design. However, like shaft and mechanical seal, stuffing box, this type of things will be important from mechanical point of view. For our point of view, from process point of view, like power requirement, then geometry, right, location, these are the important things. So this is how basically an agitator will look like, right? Agitated tank. So you can see what are the different parts. So one is the motor, this one is the motor, this one is speed reducer. So basically there is a like a gear assembly, so speed reduction drive. So motor is however rotating at the higher speed, so there is some gear down ratio 1 by 15. So you are reducing the rotation of the agitator by 15 times, right? Less like 15 times lesser, right? Similarly this is a dip leg, so which will be for a glass line reactor will be acting as a baffle. We have a jacket, this one is a baffle. So dip leg will also be used for charging the raw material also, right? This is a thermowell for sensing the temperature of the fluid, right? This is a liquid surface, right? This is the impeller, this is the bottom drain valve. So basically whenever you are designing a reactor, so always your maximum occupancy level you should maintain somewhere around 70 to 80 for a normal reactor. If it is like, if you like mostly the reactor design, right? So first of all, from design point of view, it is very very important how you are doing the piloting study. So whenever you are given any molecule, right, during the synthesis, during the lab scale and the pilot scale, so whatever are your observation, even the keenest observation is important. So foaming is there, right? Froth layer जमा हो रहा है कि नहीं, right? Is there any layer of like solids है, कुछ coagulation हो रहा है, flocculation हो रहा है? So what is the like top layer of the liquid, is it having some suspension, right? How is the material, whether it is choking or not, what is the viscosity, what is the relation with the viscosity with temperature, whether it's increasing or decreasing, right? So even all like smallest possible observation from the lab scale or the pilot scale is useful for designing of a reactor. So suppose if it is a foaming services, addition of the reactant leads to foaming, right? So in that case, you have to operate your reactor somewhere around at 40% or even that 30% also, right? So that is how you will be scaling up the reactor based on the observation and based on the conversion achieved at the pilot or the lab scale, right? So what are the different types of flow patterns, right? So first of all, this one is the axial pattern. So you can see here your this type of agitator. So basically this is a one example is propeller, right? So what propeller does, based on the design of its blade, it will push the liquid down when it is rotating, right? So during the reactor, like sometimes like one of the example where I saw is when we did the reaction for the first time, the time for the reaction was very high than the expected. So first question was what was the direction of the agitator. So we also missed the to check the direction of the agitator. So it is always necessary, otherwise if the direction of the agitator will be different, your flow pattern will be totally different, right? So always before going for the reaction, you should check the direction of the agitator, right? So for this particular case, if it is a propeller, right, so it will be rotating in clockwise direction, right? Then only it will be pushing the liquid down, and this type of axial flow pattern will be obtained, right? So this one is a propeller. Similarly, the impeller, right, that makes angle of less than 90 degree with the plane of rotation, and because of that your axial flow will take place. So this type of flow pattern is useful where you are using some solids are there, like suppose you are using some catalyst powder is there, or any solid material is there, right, suspended solid is there. So in this case you don't want your solid to get suspended, so in that case you will be using axial flow patterns. So you can use a propeller, you can also use a pitch blade turbine, right? So more energy efficient than radial flow. Here your viscosity will also be lesser, right? So this propeller can be used only for low viscous material because the size of the propeller is comparatively lesser, right? The diameter of impeller to the diameter of the tank is lesser. It is somewhere around 30 to 50%. So in that case, the material, less viscous material only it can handle because of this particular axial pattern. Because if the material is viscous, then near the walls of the reactor, you will not be able to get the desired agitation, right? So it is more effective at lifting the solids and for the low viscous material, right? Next one is the radial flow impellers, right? So basically which push the reactant mass, or you can say the material inside the reactor towards the boundary, right, towards the wall of the vessel. So that is basically the radial. So basically the turbine type of agitators, right? So you can see this is a side view and the top view. So pedals or the turbines are basically used to generate this radial flow patterns, right? So it basically pushes the material outwards of the vessel, and higher energy is required compared to the axial flow impellers because the area exposed, right, the area of the impeller that is exposed to the liquid surface is comparatively higher, right? So good amount of energy is required for pushing the material towards the wall. And also you can see like this type of basically the turbine type of agitators, the diameter of agitator to the diameter of tank is comparatively higher. So this type of agitators are used with gas dispersion whenever you want to disperse the gas in the bottom of the tank, right? So in that case you will be using the radial flow impellers, right? The next one and the last one, right, is a tangential flow. So where like a vortex will be found basically, and your this type of flow pattern will be generated. So where all your liquid or all your reaction mass will be moving tangentially to the wall of the reactor. So you can see how the swirling is happening, right? There is no like relatively, suppose at point P is equal to point A and point B, there are two different particles or the molecules are there, right? So distance between those two will always remain same. There will be no relative motion between them. So जैसे आपका point A आगे बढ़ेगा, similarly at the same velocity और point B will be rotating. So आपका कैसा होगा? It will keep on circulating. There will be no like Reynolds number will be very less because the flow will be laminar and your rotations will also be very less. So this type, can anyone tell me this type of vegetation where you can see this type of vegetation जहां पे आपका रिएक्टर के वॉल के साथ मटेरियल स्लोली मूव होता रहता है, राइट? वेयर यू हैव ऑब्जर्व दिस टाइप ऑफ वेजिटेशन, एनीवन?
Glass line react.
सॉरी,
High viscosity applications.
यस करेक्ट, हाई विस्कोसिटी एप्लीकेशन. लेकिन कौन सा पर्टिकुलर केस में आप यूज करेंगे? व्हाट टाइप ऑफ ऑपरेशन, यूनिट ऑपरेशन?
Maybe in crystallization.
Crystallization.
क्रिस्टलाइजेशन, करेक्ट, एग्जैक्टली. सो आप देखते होंगे क्रिस्टलाइजेशन में आप क्या करते हैं, यू आर नॉट बेसिकली एजिटेटिंग द मास, आप सिर्फ उसको मूव कर रहे हो स्लोली. बिकॉज अगर क्रिस्टलाइजेशन में आपने एजिटेशन किया तो व्हाट विल हैपन, योर क्रिस्टल्स विल ब्रेक, योर क्रिस्टल्स विल गेट डैमेज. तो आप क्या करते हो क्रिस्टलाइजेशन में, यू आर जस्ट मूविंग द मास, आप सिर्फ उसको मूव कर रहे हो, यू आर नॉट एजिटेटिंग इट. सो आप देखेंगे जब आपका एंकर मूव होता है तो एंकर के ऊपर सारा जो भी आपका क्रिस्टलाइज पाउडर है या आपका जो भी प्रोडक्ट है, स्लरी है, राइट, along with the solvent or the anti solvent whatever you have added, so it will keep on moving tangential pattern में it will move, right? So that is a perfect example of tangential flow pattern, right? So during the mixing vortex are formed, right?
I have one question. Excuse me.
Yes.
I have one question. But when you calculate the Reynolds number using an anchor type agitator, you will get a very good Reynolds number. Because anchor type agitator are used for high heat transfer operations. So how would you explain that?
So basically, when you are saying the heat transfer, so correct, you are using the this uh, anchor type agitator for better heat transfer. So at what cost? The movement like near the wall, it is higher, but the relative velocity between the two particles, or you can say two different points, it is zero, right? So when we talk about the agitation, you cannot say it is agitation. It is basically you are moving the velocity. You can say the tip speed is higher. लेकिन आपका दो पॉइंट है, सपोज यू आर टू डिफरेंट पॉइंट्स है, इमेजिन अ क्रिस्टलाइजर एट टू डिफरेंट पॉइंट्स, यू आर टू डिफरेंट ब्लैक स्पॉट्स या दो पॉइंट ए एंड पॉइंट बी है, इट विल कीप ऑन सर्कुलेटिंग, आप उसको
Okay.
लाइक यू कैन एजिटेट फॉर हाफ एन आवर, बट द डिस्टेंस बिटवीन दोज टू, रिलेटिव वेलोसिटी बिटवीन दोज टू विल बी कांस्टेंट। लेकिन जबकि आप वॉल से, व्हाई द एजिटेटर एंकर का क्लियरेंस वॉल से क्यों कम रहता है? बिकॉज इट इज कंटिन्यूसली स्वाइपिंग थ्रू द वॉल ऑफ द एजिटेटर। आप क्या कर रहे हो, मटेरियल को वॉल पे चिपकने का मौका ही नहीं दे रहे हो, राइट? यू आर वाइपिंग, सो इट इज जस्ट
Correct.
लाइक
Correct.
वाइप फिल्म इवोपरेटर जैसा काम कर रहा है, यू कैन से। सो व्हाट यू आर डूइंग इज यू आर कंटिन्यूसली मूविंग द मटेरियल through the wall of the reactor, so in that way you are providing the Reynolds number. But when we talk about the movement inside the reactor from mass transfer point of view, so your Reynolds number is poor. Is it clear?
Yes, yes, I got your point. Yes.
Okay.
Sir, one more application is that suppose if the material is coming from the tank with a certain flow rate like 100 meter cube per hour, which is going to the pump suction of the
Correct.
pump. So there the velocity distribution will be very effectively playing a role. So to have a constant velocity, we need to provide the tank outlet. We should have a vertex breaker. So
Correct.
can we say, sir, this kind of application also be utilized in that such flow pattern?
I mean, I didn't get exactly what you said. Can you please repeat?
From any vessel, which is connecting a pump section.
Correct.
So suppose the tank is continuously receiving a liquid, certain X amount of liquid flow rate, say example 100 meter cube per hour, and that is wanted to pump to the another location using a transfer pump. So in that case, this vertex breaker will be utilized.
Correct.
So this vertex breaker at the pump section, not means I mean the pump, the tank outlet will be provided this vertex breaker to provide a constant velocity. Okay, is it
Because
the
I
same
actually
kind
think whenever you are taking the suction, right? So good amount of velocity we are considering in the pump suction. Like I think like during the whenever like you are using the centrifugal pump, right? So centrifugal pump itself will boost the velocity. So I think during that particular thing you don't need any vortex breaker.
but usually the tank's bottom will have this vertex.
Bottom is basically given so that agitated tank is there, right? See, vortex breaker is required only where there is a agitated tank, right? If it is a normal storage tank, so there is no use of vortex breaker. Suppose there are some solids coming in your tank, right, but you don't have any agitator, right?
Ah.
So just keeping a vortex breaker without any agitator, it's of no use. Is it clear my
In
point?
storage tank, in storage tank only without agitator, there is not any vortex formation.
Yes, like basically some like what he is saying is जब आप टैंक खाली करते हो ना, तो टैंक खाली करते हो तो आपको एक swirling motion दिखता है, like you are suppose you are draining the tank, suddenly you are opening, so but without any agitator, vortex breaker is of no use. Is it clear?
Yes, yes, sir. Yes.
Okay. So what is basically vortex, right? So is it desired? Vortex are desired or it is undesired in mixing?
Undesired, sir.
Correct. So basically, vortex is nothing but basically a phenomena where your vortex is formed basically where your mixing pattern is a standstill, right? Suppose आप जैसे कि simple एक example देता हूँ, right? So wherever vortex formation is there, you can see the flow pattern. आपको laminarity दिखेगा, right? You can easily see. Suppose there is one tank which has some vortex, right? Vortex formed inside. So what will happen? It is similar again. The relative velocity between the particles will be constant, right? तो आप एक जो agitated tank है उसमें आप पानी है एक one is a agitated tank, good mixed tank, and one is a tank with vortex formation. अगर आप उसमें एक में इंक का ड्रॉप डालेंगे दूसरे टैंक में भी इंक का ड्रॉप डालेंगे सो डिस्पर्शन आपका एजिटेड टैंक में अच्छा होगा वेयर इज इन द टैंक वेयर वर्टेक्स फॉर्मेशन विल बी हैपनिंग सो वहां पे आपको क्या होगा टू गेट द डिजायर्ड बेसिकली द डिस्पर्शन ऑफ द इंक इनसाइड दैट पर्टिकुलर वाटर वेसल और वाटर का जो भी आपका बीकर है और द रिएक्टर है इट विल टेक टाइम सो व्हाट हैपेंस जैसे ही आप इंक का ड्रॉप डालेंगे so it will be dispersed in just within the vortex only, right? It will not be uniform throughout, right? So basically vortex it disturbs the uniformity of the reactor, right? So what are the methods to prevent the vortex? So it is basically one is the baffling, one is the impeller of an off angular position, so we will see. So first one is providing the baffles, right? So baffles क्या करेगा? Your vortex formation it will break. It will like whatever the eddies are there, or you can say the uh, flow patterns are there. So it will break those eddies. It will break those flow currents and disturb the motion, and it will result into some velocity and ultimately higher Reynolds number, right? So you can see how this baffles are utilized to create the flow pattern, right? See,
I just have one question regarding the vortex formation phenomena. When you say vortex, what is happening is basically the velocity from the wall to your agitator side. All the layer are having different velocities, and which is why the relative movement of these layers are different. But in this whole concentric part, the velocity is almost constant. So
yes,
so that is the reason why you're telling vortex is happening.
yes, correct.
Okay.
So
So
basically, it
that
is
being
similar
said,
to boundary layer. You know the boundary layer formation.
yes, yes, I understand. That will depends on the completely depend on the Reynolds number. So
Correct. So basically, what happens? Reynolds number is desired definitely, but it should be same uniform throughout the reactor. But in this case, what happens whenever your impeller is not properly designed, the D by D ratio, diameter of impeller to the diameter of tank, if it is very less, then what will happen? आपका center में agitation हो रहा है at a very high velocity, but
hmm,
आपका walls पे कुछ movement ही
hmm.
नहीं है, right? So that is basically vortex
हाँ,
formation.
मतलब लिक्विड एक बार आपका ये एजिटेटर से दूर जा रहा है तो उसको कोई तोड़ नहीं रहा है, वो सर्कुलर मोशन में जा रहा है, सिंपल।
Correct,
अप
correct.
डाउन पंपिंग नहीं हो रहा
Yes,
है, अप
at the
डाउन
center
पंपिंग
of the
नहीं हो रहा है
reactor,
उसमें।
at the center of the reactor, good amount of vegetation is there, but towards the boundary कुछ नहीं है आपका.
हाँ, मतलब जैसे लिक्विड आपके एजिटेशन कांटेक्ट में आ रहा है, वो वॉल के साइड चला जा रहा है, जिसमें से एक वेलोसिटी का पैटर्न बन जा रहा है, और वो कंटिन्यूअसली उसी पैटर्न में
Correct.
मूव कर रहा है,
Yes.
लेयर एक दूसरे के ऊपर स्लाइड कर रहे हैं।
Yes, yes,
यही ना?
exactly. Yes, correct.
ठीक है, ठीक। ओके।
Okay. तो बेसिकली आप कभी देखेंगे ना, जस्ट सिंपल वेरी वेरी सिंपल एग्जांपल, व्हेनेवर यू आर सपोज आप थोड़ा लाइक सॉल्ट राइट ब्लैक पेपर या सॉल्ट आप ले लो राइट कीप इट इन द बेसिकली इन द ग्लास आप बीकर ग्लास के ग्लास नॉर्मल ट्रांसपेरेंट ग्लास एंड यू स्टर आप स्टरिंग रॉड या स्पून से स्टर करो और एक ही पैटर्न में कंटिन्यू स्टर करो एट हाई आरपीएम राइट यू विल सी द सॉलिड्स विल गेट सेटल इन द बॉटम एक ही जगह पे सब जमा हो जाएंगे राइट आप कभी कभी क्या करते हो बॉटम में जो भी आप कचरा है सपोज यू आर ड्रिंकिंग एनी बेवरेज राइट आप कुछ भी पी रहे हो जहाँ पे लाइक बॉटम में कुछ सॉलिड्स आर देयर राइट वॉट एवर द ड्राई फ्रूट इज देयर सो आप क्या करते हो बॉटम में उसको शेक करके यू ड्रिंक इट राइट सो व्हाट इज हैपनिंग एट वोर्टेक्स फॉर्मेशन में क्या होता है the vortex basically whatever the suspended solids are there catalyst particles हो सकते हैं या raw material हो सकता है because of the vortex they will get settled down in the bottom right so bottom में जमा हो जाएंगे, it will not be dispersed phase. So that is one of the phenomena you can say which is undesired because of the vortex formation. Okay,
बिकॉज वो सबसे लो प्रेशर जोन होगा तो वहां पे सेटलिंग होगा, आप ये बोल रहे हो ना?
करेक्ट, जहां पे उसको कुछ ड्राइविंग लाइक नो फोर्स इज अप्लाइड फॉर द मूवमेंट, राइट, तो उधर उसको कोई मतलब छूने ही नहीं जा रहा है उसको, लाइक इट इज गेटिंग नो बेसिकली फ्लो, राइट, उसका फ्लो पैटर्न कुछ है ही नहीं उधर, so that's why it will get settled down.
ओके।
So you can see basically, right, so just one another thing, like vortex, like what happens, like the axis of rotation is there na, so suppose आप same agitator में कम rpm पे rotate करेंगे ना, so it will not form vortex. Vortex will generally happen at higher velocities. Desired velocity से आप ज्यादा करेंगे या ये आपका impeller का size कम है, so in that case only vortex will happen. So what will happen, आपके particles इतना fast move करने लगते हैं, it will like formation of a cyclone, राइट, अगर नॉर्मल विंड इज ब्लोइंग सो देयर इज नॉट एन इश्यू, लेकिन जैसे साइक्लोन कैसे आता है, इन वन पर्टिकुलर लाइक मोशन द पार्टिकल्स आर मूविंग कंटिन्यूअसली, so it will lead to a settling of the particles at the bottom, right? So you can see here how the baffles are there and see there is a flow pattern, so how it is breaking the flow pattern and it is creating some turbulence, right? So this is one of the baffle, so this is a direct contact baffle, this one is a baffle which is like offset, this one is the angular one, so this one is a far away from the wall, so top mounted है और distance भी है इसमें, distance between the like bottom में connected और top में connected, so there is some distance between the reactor and the baffle, and this one is the angular one. So you can see here there are the three different categories. This one is a normal one, so this is a top view and side view, and this one is the angular one, and ये जो है D type, so this one is a D type, right? So you can see how your eddies or your flow currents are broken by the vortex, by the baffles, right? So this is the phenomena which is happening. See, because of the vortex formation, आपके सारे solids एक ही जगह पे आ गए, right? So we want this type of dispersion, right? So this is one is with the baffles. You can see these are the baffles, right? These are the picture taken actually, right, in a glass beaker. So you can see here. So ये है vortex formation, right? So poor distribution because of the vortex formation. Clear? What you can do is, second option is, if you don't want to put the baffles, then you have to put your agitator at the offset, right? So many times आपने देखा होगा where there is like आपका suspension बन जाता है, where there is like particles are also there and it gets suspended. Top से आप कुछ offset पे mute yourself. ओके, सो आपने देखा होगा कि या तो एंगल में या फिर ऑफसेट पे आप एजिटर लगाते हो, सो व्हाट इट विल डू, इट विल बेसिकली लीड टू ब्रेकिंग द वोर्टेक्स, राइट? सो देयर विल बी सम imbalance of the force from the center of the axis, you are moving away, so basically because of the imbalance of the forces your vortex formation will not happen, right? So you can see here, right? So यहाँ पर एंगल में है, यहाँ पे ऑफसेट है, so it is dispersed, right? So now we will move to the main topic. So what are the types of agitators, selection of the agitators, right? So if you have any query, you can interrupt me and ask, right? यहाँ तक तो क्लियर है ना सबको?
अच्छा, एक मेरा क्वेरी है, if I want to see that there is a chance of vortex formation, क्या मेरे को मेरा टिप स्पीड उधर से कुछ है क्या, टिप स्पीड से, या फिर कोई नॉन डायनामिक नंबर होगा जिससे हमको पता चल पाएगा कि हाँ इसमें वोटेक्स फॉर्म होने की पॉसिबिलिटी बनती है वैसे?
Yes, definitely. Just basically the tip speed is the only thing, right? Which is basically governing tip speed as well as the diameter of the agitator. So अगर आपको लैब में basically if you are getting the vortex, then definitely at that particular tip speed you can also get at the commercial scale also. So just आप देखना कभी observe करेंगे, right? If your agitator diameter is bigger, right, and it is rotating at some RPM, if the same agitator, right, if it rotates at higher RPM, then it might create vortex, और अगर आपका agitator like tip speed, like basically it's a game of rotation only, so with the same agitator at higher velocity it is forming the vortex. So you need to take care ki what is the basically diameter of agitator to the diameter of the tank, which is the optimum desired for the desired power by volume ratios, you can say, or the tip speed, you can say, which is giving you the desired mixing but not leading to the formation of vortex, right? So in that way you need to design.
Okay.
So if the agitator is too small, see, basically what happens, your mixing totally depends on RPM as well as the diameter of the agitator, right? Higher the diameter of the agitator, higher will be your mixing or agitation, or higher the RPM, higher will be your mixing. लेकिन सपोज डायमीटर जैसे मैंने बोला एंकर का, तो एंकर का डायमीटर तो काफी है लेकिन मिक्सिंग वो इतना नहीं दे पाता, क्यों? बिकॉज इट्स आरपीएम इज वेरी लेस, राइट? सिमिलरली इफ यू हैव अ प्रोपेलर, राइट, सो प्रोपेलर का डायमीटर काफी छोटा है बट बिकॉज ऑफ द हाई स्पीड इट माइट अगेन लीड टू वर्टेक्स फॉर्मेशन. सो आप देखना ऑप्टिमम बिटवीन द प्रोपेलर एंड द बेसिकली दिस एंकर इज समवेयर अराउंड, जहां पे आपका डी बाई डी रेशियो इट इज समवेयर अराउंड 50 to 60%, राइट? डायमीटर ऑफ टैंक से इट इज 60 to 70% या 50 to 70% के बीच में, जहां पे इंपेलर का डायमीटर होगा, राइट? योर इंपेलर डायमीटर इज 0.5 से 0.7 टाइम्स द diameter of the reactor. So in that case you will find vortex formation या इस टाइप के cases scenario कभी नहीं आते. If your diameter is too large or it is too small, then only this vortex formation and tangential flow patterns will come into picture. Is it clear?
Yes, yes, yes.
Okay. So what are the types of agitators? It is pedals, propellers, turbines, helical ribbons, tooth या disc type and cone type, right? So this starting with the pedals. So pedals में क्या क्या आता है? So you will get all the types of turbines, flat blade, 4, 2, 6, all types of rust and disc. These all things will come in pedals. So where they are suitable? So they are suitable for stirring the simple liquids, right? So moderate speed जहाँ पे 20 से 150 RPM है. Even somewhere around 180 also they are used. So they push the liquid radially. So हमने देखा radial flow. So that is the example of pedals. So anchor is one of the pedal type, right? So these are the anchors, right? This is the two blade, flat blade pedal, right? So the ratio of pedal diameter is somewhere between 50 to 80%. Whereas for the anchor, it is somewhere around 90 or even 95 also, you can say 90% जितना रहता है. Very minimum clearance is there, right? Somewhere around 50 clearance रहता है. So that is a good amount of percentage है. So that is the exceptional case. But mostly जो flat bed pedals की बात करें, so it is somewhere around 50 to 80% of the tank diameter. So speed range, right? So it is somewhere around 5 to 300 used for large vessels, right? So agitator size almost touching the vessel wall. So that is basically they are talking about the anchor. So pedal type आपने this type of agitator you will see in dyes industries, pharma industries में आपको anchor मिलेगा, right? So wherever like solid powders are there, suspension is there, right? And you want the like product is there as a product like in a suspension, and your particle size is important, right? You don't want to disturb that. So in that case these pedals will be used. So mostly dyes industries as well as the pharma, right, they use this type of pedals, right? So it does not, like when we talk about the anchor, it does not allow the solid buildup on the wall, right? Used for reaction vessel having jacket by providing good heat transfer area. So that's the reason anchor is used. So basically what happens, anchor continuously keeps on sweeping the material from the wall of the reactor and ultimately enhancing the heat transfer, correct? So you can see what are the different types of anchors that are available. So this one is the anchor, normal anchor, this is a gate type anchor, right? Anchor pitched anchor is there. So these blades are in the angular form, right? This one is the anchor with cross arm. So there is one rotating this one also basically for like to provide the mixing, right? So these are the special designs, right? Next one is the propeller, right? So propeller is basically used for low viscosity fluids, right, where your RPMs are also higher, right? So these are used where your L by D ratio is higher, right, and you want axial mixing, right? Generally pedals में आपका L by D ratio कम होगा, right, where your tanks are bigger in size, जहाँ पे when you go in dice industries ना, your reactors or basically your stir tanks are as high as 50 or 100 kl, right? So in that case you are using this flat blade pedals, right? Whereas in propellers, when like autoclave is there, right, where your small reactor is there, where your L by D ratio is higher, where kettle is there, so in that case you can use the propeller. It will give you good amount of axial flow जहाँ पे आपका suspended solids है, right? So they are used for deep tanks, right? So for low viscosity fluids, right? So you can use this type of basically propellers with somewhere around up to 3-4 kl तक आप use कर सकते हो, even 5 kl तक कोई issue नहीं है, right? Above that propeller gets replaced with the pitch blade turbine, right? So maximum speed is you can go up to 400 rpm also, right? And the diameter of propeller is very less compared to the diameter of the vessel, right? So it is somewhere around 15 to 30% of the vessel diameter, right? So these are the turbines, right? So turbines यानी कि क्या है? It's basically diameter is somewhere around 50 to 30% of the vessel diameter, right? Suitable for wide range of viscosity, low से लेके high तक, right? And tangential as well as radial mixing patterns are generated. So you have this disc type, right? Disc type turbine. So this is the disc and the turbine, right? So why this shape is given? पूरा का पूरा उसको flat भी रख सकते थे. So basically this is with respect to power consumption. So when you compare the straight turbine blade, right, the area, right, it is higher comparatively, area exposed to liquid is higher, so good amount of power is required for this particular turbine compared to the disc type, right? Similarly when we talk about the pitch blade, so pitch blade में आपको axial plus radial का combination मिलेगा. Here your power consumption will be significantly lower, right? Next one is this one is the concave blade, six blade impeller. So this one is again the special case. So like wherever your requirement is like changing, or wherever you want a desired you can say mixing flow pattern, so you can use this type. Otherwise the most common one is the pitch blade only, right? This one is the highly used. So like this type of agitator you can use like in the bottom of the tank, wherever your suspended solids are there, you can use it as a tickler. तो मोस्टली कहाँ पे रिएक्शन होने के बाद देयर इज सम impurities or sludge formation, right? So at the immediate bottom of the tank, right, very small tickler is used. Somewhere around उसका कितना 200 mm will 200 mm will be the radius, somewhere around 300 to 400 mm will be the diameter. So that type of small tickler is used, right, in big reactors to avoid any deposition of solid in the bottoms, right?
Straight blade turbine is a paddle type.
Yes, this one is a paddle type, but it like it's a turbine category turbine ही रहेगा उसका. Like it's a, you can say turbine is basically, see, definitely it's a paddle type only, but it basically comes in the turbine one. और यहाँ पे जो यहाँ पे if it is saying ना straight blade turbine, so if it is 2 then it is a paddle. यहाँ पे straight blade turbine में आपको 6 will be there, 6 flat blade है. So it will be like this. This is the flat blade. ये जो बोल रहा है ना, ये 6 है उसमें. That's why it is called turbine. अगर 2 ही होते तो it is a type of paddle only basically. Clear है?
Okay.
DA by D ratio will also be changed, no?
Sorry.
मतलब diameter of agitator to the diameter of tank ratio will also be different in both
Yes,
the
वो
cases.
हम देखेंगे. Just हम like we are running short of time. No issues. We will extend it. So that part is coming. We will discuss everything related to the agitation. मैं बताता हूँ आपको. Just a few more minutes to go. Okay. तो बेसिकली टर्बाइन टाइप आपको एक्सेल फ्लो पैटर्न देगा. सो दैट विल बी बेसिकली पिच ब्लेड टर्बाइन, और रेडियल के लिए फ्लैट ब्लेड है, राइट? सो दीज आर द डिफरेंट टाइप्स ऑफ टर्बाइंस, राइट? So I'll just move quickly, right? We are having good amount of discussion pending. So if you have any questions, you can definitely interrupt me, right? अगर कुछ समझ में ना है तो बताना. So these are the different types of turbines, right? Based on the application, what type of shear rate you want, right? So higher your viscosity, higher dispersion is required, right? Mostly turbines हम use करते हैं जहाँ पे आपको dispersion चाहिए, dispersion of gas phase, right? So in that case, you will use you will increase the amount of blades if you want better dispersion and better shear rate, right? Again, helical ribbons, it is again used where your desired shear rate is higher and your viscosity is higher. So very simple example is like in food industries, right? So in food industry, wherever you are having this you can say like जहाँ पे हम पिज्जा का डो बनाते हैं, right? You are making the bread, right? So bread industries में, food industries में, you will use this type of helical ribble type of agitator where you are blending. So in that case, this high viscosity applications, higher shear rate you want, right? Suppose you have this industry you can say like a toothpaste industry, right? So where viscosity is higher, in that case you can use this type of helical ribbon, single, double, right? So for pseudoplastic materials, and the power requirement is also high because of the higher viscosity. So you can see what are the different types of helical ribbons. So it is nothing but a type of blades only, right? Different blades will keep on mixing, spiral helicals, double helicals, right? So agitator selection, it basically depends on viscosity, right? It is one of the factor, right? So propellers are used for very low viscosity, right? 3000 centipoise and below. Turbines can be moderately somewhere around you can say 1 lakh centipoise, right, and below. And anchors, right, they can used to about 50 से लेके 500 तक, uh, like sorry 5 lakh तक, right? 50 से 5 pascal second up to 5 lakh you can use the anchors. And helical ribbons, right, they are used for the highest viscosity, right? So it is from 1000 pascal second to 25,000 pascal second, right? So this is basically the criteria. Lowest के लिए propeller, then comes the turbines, then comes the anchors, and then the helical ribbons, right? So this is the selection criteria, right? So this is the viscosity in pascal seconds, right? So you can see turbine hai, impeller hai, right? Pitch blade turbine, propeller for the lower viscosity. Then comes the different types of anchors, and you can see this Ikato, Intermediate. Ikato is a good, like it's an organization, it's a company manufacturing the agitators, right? So Ikato is manufacturing the based on the customer requirement, different types of desired agitators, right? So that you can use for somewhere on moderate viscosity, and for high viscosity anchors and ribbons, right? So this is the criteria with respect to viscosity. Now with respect to the flow patterns, right, and application, right? So impeller, this one is like pitch blade impeller, so you can see, so high efficiency impeller, right, for blending, turbulent heat transfer, solid suspension. So pitch blade is used where your power number, right, it will be 0.27 and your flow number will be 0.5 for this particular impeller. So whenever you are designing this pitch blade, so there should be your power number, right? Similarly, this pitch blade turbine, four blades. So mostly pitch blade with pitch blade turbine with four blades, 4 PBD is the most common one, right? So आपने काफी बार देखा होगा कि हम बोलते हैं कि pitch blade turbine के लिए power number आप 1.2 ले लो. So that is the reason your power number for this particular agitator, right? Because power number is factor of RPM, it's a factor of diameter, right, density. So based on that, based on the you can say lab experiment as well as based on the history, right, for different agitators, this particular 4 pitch blade turbine, it gives good amount of desired agitation with minimum power requirement at np is equal to 1.25 and flow number at 0.7. So it is again used for blending, dispersion, suspension. So wherever axial flow is there, you are using that particular agitator for dispersion and suspension, right? Next one is the flat blade turbine, right, for with 4 blades, S4. So it is for dispersion, keeping outlets near from solids, right? So where your see power requirement is increasing because your it is coming towards the flat blade, right? So power number is 3. Similarly, like a wide blade, max flow T. So that is again a very small, you can say like a combination of like it's a type of propeller, right? So for blending, gas dispersion, solid suspension, it is used, right? Again, this one is the cam shear type, right? For liquid dispersion, right? So here again shear rate will be higher. Then this one is a Ruston turbine, so 6 blade turbine. So for again for the gas dispersion, so mostly turbines will be used for dispersion, propellers for the axial flow, and PBTs for the suspensions, right? So you can see for the turbine also NP is provided. So this is one of the uh, chart basically for the selection of the agitator. Otherwise, however, like PBT, right? Multiple PBTs are used to basically uh, in a reactor. PBT in combination with RCI, right? Retreat curved impeller, 3 RCI and 4 PBT is the most standard combination, right? Next one is the concave disc turbine, right? Again for the gas dispersion. So mostly all the turbines you will use for dispersion. Helical ribbons for blending, right? For high viscosity fluids, right? Anchor again for viscous media, basically crystallizers, right? Then this one is the again the turbines for gas dispersion, right? So this is about the different types of agitators, right? Based on the flow patterns, based on the number of blades and type, right? Now this one is with respect to the MOC as well as the flow pattern. So this one is the most common chart, right? So what type of reaction it is? If it is a homogeneous reaction, if it is acidic condition, acidic media, so glass line reactor Hastoloi. With low viscosity, go with PBT, flat turbine, disc blade turbine, or RCB, right? So that is a curved blade, right? Retreat curved blade. Medium viscosity के लिए PBT, anchor and RCB, and high viscosity के लिए anchor. So these are the most common. Like this chart is taken from one of the from the design philosophy and a guideline from one of the industry, right? So PBT, right? Disc blade, then anchor. These are the most common choices. Similarly, if it's a basic media, go with SS or Hastoloi, right? For the same again low, medium, and high viscosity, the selection choices are again same, right? Similarly for the heterogeneous, now heterogeneous matlab kya hoga? Solids are coming into picture, right? Your liquid solid basically reaction will be there, right? Your catalysis will be there. So catalyst will be in powder form. So in that case, heterogeneous catalysis you will be using in acid or base condition, right? With solid, without solid, right? So solid hai ab hydrogenation example. So glass line reactor Hastoloi with gas induction turbine or the propeller with good amount of axial flow, right? If solids are not there, then again the case will be same as that of this homogeneous case, right? Similarly for the basic media also, the MOCs are same, right? But जहाँ पे आपका solid आएगा, where there you will be using the gas induction turbine, right? So gas induction turbine is like basically providing good amount of basically dispersion for the gas. So जहाँ पे भी hydrogenation use कर रहे हो, so in that case you will be using gas induction turbine or gas induction propellers, right? Now with respect to the type of reactor and type of application, right? So axial flow में आपको pitch blade मिलेगा, retreat curve impeller मिलेगा RCI, marine turbine मिलेगा, twin agitator मिलेगा. So based on the type of reactor, right? RCI is most common with the glass line only, right? So यहाँ पे आपको क्या करना है? So most common, these all are common, like homogeneity, suspension, liquid, solid liquid, right? Gas liquid dispersion. So pitch blade turbine है तो gas liquid dispersion के लिए होगा. Whereas RCI, तो it will not be for the gas liquid dispersion because it is providing you the it is basically RCI is for the liquid mixing only. Similarly, marine blade, it will give you gas liquid dispersion, right? So these are the criteria. What is the desired application? Based on that, you can decide. Similarly, you can see here anchor. It is provided for homogeneity and for the heat transfer, right? Similarly, flat blade and disc blade are used for heat transfer for the solid suspensions, solid liquid, right? So this one is again one of the criteria with respect to power numbers. So with different types of blades, your power number is changing, flow number is changing. So here the standard D by T ratios are mentioned, right? So you can see D by T ratio for the Ruston is somewhere around 0.33. Similarly, W by T is basically the width by diameter of the tank, and D by T is diameter of the impeller with diameter of the tank, right? So W by T and D by T, mostly it is fixed for the six blade turbines, right? We will see, we'll do one designing example for that six blade turbine also. Similarly, for different types of impeller, with respect to the number of blades, right? So you can see the power numbers, right? You can see one interesting thing, right? So here there is a pedal with two blades and four blades. So you can see here with two blades the number of the power number is 5.4, but with four blades it is reducing. So see how the like power requirement is higher with respect to, like it is not the case with जैसे रस्टन में कैसा हो रहा है, ब्लेड आपने बढ़ाया, right, you increase the blade, then in that case आपका पावर नंबर बढ़ा, बट दैट इज नॉट द केस विद पेडल्स, बिकॉज आपका जब पेडल रहेगा when your blades are lesser, so in that case all the force of the fluid will be acting on that basically the blade only. So in that case your power number with two blades will be higher, right? With four number of blades comparatively your basically your flowability will be increased, so you will require comparatively lesser power with respect to four blades, right? So that is one of the interesting thing to observe, right? Similarly, for different other types of agitators, right, what are the different power numbers that is provided, right? So what are the different factors affecting the power requirement, right? So that we already saw. So what are the different dimension analysis, right? So जैसे कि diameter is the characteristic length, time यानी कि क्या है, it is inverse of the speed, so it is basically the unit is second. Similarly, when we talk about the mass, तो mass मतलब क्या है आपका, density is kg per meter cube and diameter cube is volume, so basically rho d cube is basically giving you the mass. Similarly, what are the different other quantities, जैसे कि dn diameter multiply by the speed or the rpm, it is giving you the velocity, right? So these are the different derived quantities, and based on these you will get the dimensionless numbers, right? So why dimensionless numbers are useful? So basically they help us to derive some empirical correlationship to estimate the power required. Similarly, Reynolds number क्या है, it is rho v d by mu, right? Rho v d मतलब क्या हो गया, inertial forces divided by the viscous forces. So basically what dimensionless number shows is कि how your forces are dominating, right? Just giving you a very simple example, जैसे कि प्रांटल नंबर क्या होता है, cp mu by k. So where mu is there, so it is viscous force conductivity dominate करेगा. So when we talk about glycerin, so there your viscosity is dominating, so heat transfer will be very poor with glycerin, right? Similarly, when we talk about the mercury, right, so in that case your conductivity is higher, so in that case your Prandtl number cp mu by k है ना, और mercury का conductivity ज्यादा है, so your Prandtl number for the mercury will be minimum, whereas your Prandtl number for the glycerin will be higher. So basically dimensionless numbers, they are used to basically to establish a relation between the different flow patterns or different parameters, right? So what are the different dimensionless numbers used for this designing of the impeller, or you can say the agitator? Is flow number is there, so it is basically called q, that is the flow rate, divided by the ndq, where d is the diameter of the agitator and n is the rotations per minute of the agitator, right? So nq for different types of impeller is already provided, right? I will share this presentation, you can go through it, right? So these are the important dimensionless numbers. So first one is the Reynolds number, that n d square rho by mu. So here velocity has been written as nd, right? Similarly, flow number we already discussed. Power number, that is basically this is your power, then n cube, d raised to 5 and rho, and this one is a fraud number, right? So you can see this one is a power number. So power number with respect to Reynolds number, you can see where your Reynolds number is poor, right? In the laminar region your power number is higher, it means your power consumption is higher. So whenever your laminar flow is there, what does this mean? Reynolds number yani ki C rho v d by mu. So when your viscosity is higher, your Reynolds number will be lesser. So it will be basically a laminar flow. So laminar flow में किसी भी चीज को मूव करना is very difficult, right? जैसे कि आपका टूथपेस्ट है और your glycerin is there, right? So very highly viscous material, you require more energy to move. That's why your power number is higher. Once you go from this laminar region से आप बाहर आ गए, right? So you see what is a drastic change in the power requirement, right? So आपने काफी बार देखा होगा कि whenever your reaction mass is happening, right, you are adding some solvent, right? So many times whenever you are producing any like product you are manufacturing, so you will be adding some solvent. It may be benzene or toluene or methanol or heptane or different types of solvents you are adding. So why you are adding those solvents? Because your reaction mass becomes very highly viscous after reaction. So in order to reduce those viscosity, reduce the power consumption, right, for proper mixing, reduce the batch cycle time, we are adding the solvent to reduce the viscosity, the overall viscosity, to improve the flowability, flow patterns, and improve the Reynolds number. That's why we are adding solvents, even though solvent is not taking part in the reaction, right? Similarly, with respect to flow number, you can see the flow number increases with the turbulent flow. So it shows how your flowability is there with respect to diameter of the tank and your RPM, right? Similarly, blend time is there. So you can see blend time is higher in Reynolds number, right? So blend time yani kya hai? T blend time multiplied by your RPM. So in laminar region, your blend time is higher. In turbulent region, your blend time is lesser, right? So power consumption, right? So basically this is the equation where P is your power, NP is your power number, this is your RPM, diameter, density, and this is a gravitational constant, right? So we have different curves basically, right? So this one is the curve for the power number, right, for the 6 blade turbine, right? So these are the four different curves A, B, C, D, right, with four baffles are there, right, and D is for the unbaffled, right? So curve ABC for baffled and D for unbaffled. So when you want to scale up this agitator, right, आपने lab scale में pilot plant में आपने 6 blade turbine use किया, right? Now you want to scale up at commercial level. So one of the parameter can be constant power by volume ratio, right? So in that case what you can do is आपका power number उधर और इधर आप same रखेंगे. So power number will be same. So in that case what will happen? Right, you will calculate the power number here, right? So suppose if I keep power number np is equal to जो भी 1.2 है, right, then from that I will calculate, I know the RPM, I will know the diameter of the agitator, right, from the scale up density. So from that I can get the power, right? So how for the corrected power number I want, right, there is some correction, so fraud number will be used. So which correlation will be used? Your corrected power number will be equal to power number multiplied by fraud number raised to m, where m is equal to a minus log 10 nre by b. So where your a and b are some constant basically for the non-idealities, right? So what are a and b, right? So these are the a and b, at different a and b, right? So you can see for different types, diameter of the agitator, turbine or propeller, di by dt ratio is there, right? Based on that your alpha and beta values are there, a and b value, right? So you are having different curves, right? So based on that curve, based on the Reynolds number that you have found, उससे आपका power number कितना आएगा, right? Suppose let us take one example. So we'll just quickly see the chart. So this one is power number with respect to Reynolds number for 6 blade turbine, right? Similarly this one is for the standard baffled tank, right? For the unbaffled tank, right? So for the unbaffled tank you have to insert the power number correction, right? So this is the terminology. तो सबसे पहले हमने रेनॉल्ड्स नंबर फाइंड करना है. If it is baffled, then power number का इक्वेशन हम यूज करेंगे डायरेक्टली. If it is unbaffled, we will find the fraud number. So fraud number कैसे मिलेगा? n square dA by g, right? We will find m from this equation, insert the correction factor, and finally get the corrected power, right? So what is the for the 3-blade turbines? It is 1.7, A is 1.7 and 18, 6-blade के लिए 1 and 40, right? So we have this A and B factor. So let us solve one example. Right. So one example is there is a flat blade turbine with 6 blades is installed centrally in a vertical tank where your tank diameter is 1.83 meters and turbine diameter is 0.61 and it is positioned 0.61 meter from the bottom of the tank, right? So these are the different terminologies. So यहाँ पे h is the height of the basically the turbine, right? Then dt is equal to the diameter of the tank, j is equal to the thickness of the or the width of the baffle, right? Da is the diameter of agitator, E is the clearance from the bottom, right? W is the width of the agitator of the blade, L is the length of the agitator blade. So these are constant with respect to standard turbine, right? 4-blade turbine जो standard है disk type उसके लिए standard है, right? So whenever you are using, if you know the tank diameter, then you don't need to do any calculations, you have to go with this particular. So these type of standards are available for all the types of agitator, right? So based on the data, right, turbine blades का width है आपके पास, उसका diameter है, right, clearance है, it is filled, tank is filled up to 1.83 meter with a solution of 50% caustic soda. So viscosity you have, density you have, and you have the RPM. So what will be the power requirement? So first of all, you know the RPM is 90 RPM. So उसको आप convert करेंगे rotations per second, right? Will be for this particular calculation RPS is used, right? SI units. So diameter of agitator is 0.61 meter, and your viscosity is 12 centipoise converted into kg per meter second, right? So your NRE, Reynolds number, is coming out to be, from this equation it is 69,000. So for Reynolds number greater than 10,000, NP is equal to 4 from the curve. Sorry, actually here the NP is 5.8, right? Here it is 5.8. This is a mistake, right? So how it came? So you can see from this curve, right? From this particular curve, right? So here your NP is here 10 raised to 4, it is 10,000. So somewhere here it is 69, 70,000, right? So you can see here A with 4 baffles, right? So here somewhere around 6 is there, 5.8 to 6 is there, right? So 6 is your power number, right? So your power number is 5.8. So just correct it. This is not 4, actually this is 5.8, right? So once I put power number is equal to 5.8, I will get the power requirement. So it is coming out to be 2476 watts, right? Similarly, if it is unbaffled, then what I need to do? I know the Reynolds number. What will the power number? So for the unbaffled tank, again we will see what is the power number. तो अनबैफल्ड टैंक यानी कि डी, सो यहाँ पे उसका एकदम कम है, राइट? योर पावर विल बी वेरी लेस, राइट? तो अनबैफल्ड टैंक के लिए आप क्या कर रहे हैं? You are taking like here very less, it is near to 1 only, so we have taken 1.1. So for unbaffled tank, right, power number is 1.07, which is not correct. So I need to insert some correction factor, right? So I have calculated the fraud number, which is 0.14. From the table I have calculated the m value, right? A and B I know from the table, right? Standard tables. So from that your corrected value of the power number is 1.3, 1.29. From that, if I calculate power, it is coming out to be 550 watt for unbaffled tank, and for baffled tank it is higher, right? So this is how basically calculation is done for the turbine. Is it clear? Yes or no? Any doubts? Yes?
Yes.
Anyone?
Oh, no. Everything's clear.
Clear है ना सबको? Please don't hesitate while
Ah,
asking.
clear.
Okay.
No, clear.
Yes.
Right? So just one feedback from my end is also like last 2-3 times I am taking this type of webinars now. So students are also very interested and they are also coming prepared, right? So that is a very good thing. Like they are also equally interested, right? So this type of graphs you will find from the literature. So with respect to different types of agitators, what is the Reynolds number to power number? So these charts are useful for scale up with respect to power numbers, right? So this one is for the turbines and impellers, This one is for the helical ribbons, for the pseudoplastic fluids, right? High viscosity, for the pitch blade turbines, PBTs, right? For the three blade propellers, right? थ्री ब्लेड में भी क्या है कि अलग अलग P by D ratio अलग, D by DT ratio भी अलग, right? For the six blade turbines, right? So from that, this one is a standard turbine design, right? So you can refer. So now let us see what is basically how is the heat transfer taking place in a agitated tank, right? So basically your overall heat transfer coefficient, it is a summation of different components. So first one is the film, right? So first one here is the film, right? This is the process side on the right hand side. On the left hand side it is the fluid side, heat transfer fluid or utility side. So this one is the first film. So this is the film resistance because of the film of the utility. Next one is because of the fouling on the utility side. So this one is the fouling factor. Now this one is the wall of the reactor. So you will be having the conductivity, you will be having the conduction, right? So conduction because of the metallic wall, right? If there is a lining, right? So lining का भी एक conduction factor रहेगा, like you are like resistance because of the conductivity. Next one is the fouling on the process side, right? And finally film on the process side. So these are the different barriers basically for the heat transfer, right? So these are the different resistance to the heat transfer. So overall, when we see this is the overall heat transfer coefficient and your Nusselt number, right? This is the correlation for the reactor. Your Nusselt number is a uh, it's directly proportional to Reynolds number, Prandtl number, and mu ratio, right? There is the viscosity ratio, and GC is the geometry correction factor for the reactor. So we will see what that is basically. So whenever you get the overall heat transfer coefficient for a reactor or a agitated reactor with different types of agitators, right? So there you can have this. You know the Reynolds number you have, Prandtl number you can calculate. You have the viscosity ratios. Now you are left with the ABC three constants, the geometric correction factor and the K value. So that you can get from the literature, right? So with the different types of impellers listed over here, different types of surface, right? So walls is there and everything is there, right? So here Reynolds number is always greater than 100, right? K value you have, A, B, C value you have. Now what is the geometric correction factor? So 1 upon H by T. So H by T is height of the impeller to the tank. Sorry, H by T is basically the height to thickness, and L by LS, right? So once you put these values, this is a geometric correction factor. Once you put this value, you can get the Nusselt number, and Nusselt number is nothing but HD by K. So from that you can get the heat transfer coefficient H, right? So this is how the calculation is done for the heat transfer coefficient for the agitated baffled vessel, right? So I have one Excel sheet, from that I have converted, right? I will show you. Again, whenever you want to heat or cool, suppose you are given a task that there is some process material inside the reactor, right? Suppose there is 1 kL of some crude mass in the reactor, right? You have the area of the reactor, you have the overall heat transfer coefficient, right? And you are given some utility. Suppose I'm given some steam is given, right? Now I want to increase the temperature of that crude mass from 30 degree to 100 degree. I am given 3 kg pressure steam. So what will be the time it will take to heat the mass from 30 to 100 degrees? So how to calculate that? So that is basically the transient heating. Yes. Yes, Devan. Okay. Any questions?
यस सर। तो बहुत पहले का था क्वेश्चन, जो आपने रिएक्टर का जो डिजाइन दिखाया था ना, उस टाइम मेरे को एक क्वेश्चन था, वो आप बहुत आगे चले गए।
हाँ, बोलिए। नहीं, you can ask.
What is the function of gearbox and deep pipe in reactor design? वो
Deep
आपने
pipe, deep pipe तो हम raw
रिएक्टर का
material
जो डायग्राम
charging.
दिखाया था,
Sorry.
आपने रिएक्टर का जो डायग्राम दिखाया था ना, उस टाइम पे मेरे को क्वेश्चन था उसमें what is the function of a gearbox? We are providing gearbox, and what is the function of a deep pipe in reactor design?
बेसिकली डिप पाइप तो आप यूज करते हो लाइक जैसे कि ग्लास लाइन रिएक्टर है, राइट? तो ग्लास लाइन रिएक्टर में आपको बेफल्स नहीं होते, तो आप डिप पाइप डाल के you are using the dip pipe to basically to break the vortex formation या to provide the रेनॉल्ड्स नंबर बढ़ा सकते हो या आप उसको vortex formation break कर सकते हो. So baffle की जगह पे आप dip pipe यूज करते हो ग्लास लाइन रिएक्टर में. Other than that you are using the dip pipe for raw material charging, क्योंकि अगर आप ऊपर लाइक इफ यू डोंट यूज अ डिप पाइप आपके रॉ मटेरियल्स गिरेंगे, वॉलेटाइल रॉ मटेरियल्स है, सो इट विल लीड टू वेपर लॉसेस, आपके वेंट लॉसेस बढ़ जाएंगे. दैट्स व्हाई हम बॉटम में जाके डिप पाइप से हम फिलिंग करते हैं, राइट? व्हेन वी टॉक अबाउट द गियर बॉक्स, तो गियर बॉक्स मतलब क्या है? लाइक बेसिकली आपका मोटर हाई स्पीड पे घूम रहा है बट योर शाफ्ट कैन नॉट रोटेट एट दैट हाई स्पीड. तो मोटर क्या करता है? गियर रिडक्शन कर देता है, राइट? आप जैसे कि गियर है, सपोज यू आर ड्राइविंग अ बाइक, राइट? आप बाइक चलाते हो तो फर्स्ट गियर में आपको पावर ज्यादा मिलता है, राइट? वंस आपका एक पिकअप आ गया उसके बाद क्या होगा? यू आर रिड्यूसिंग योर लाइक इंक्रीजिंग योर गियर नंबर, सो आपको पावर कंजम्पशन कम हो जाएगा, आपका स्पीड बढ़ गया बट योर पावर कंजम्पशन विल बी लेसर, राइट? सो इनिशियली आपको पावर ज्यादा चाहिए या आपको लाइक बेसिकली क्या बोलते हैं वेलोसिटी चाहिए, सो बेस्ड ऑन दैट यू विल स्विच द गियर्स. सो गियर का फंक्शन ऐसा है कि मोटर का जो वेलोसिटी, मोटर आपको कभी ऐसा नहीं होगा whenever you buy the मोटर आपको 50 आरपीएम का नहीं मिलेगा, लेकिन आपको रिएक्टर 50 आरपीएम पे चलाना है, तो आप क्या करेंगे? सो देयर इज व्हाई देयर इज अ गियर असेंबली. सो बेसिकली गियर का जो डायमीटर से ये वन इज अ बिगर गियर, वन इज अ स्मॉलर गियर, सो गियर डाउन करते हैं हम, राइट? फ्रॉम 15 लाइक 15 to 1 इज द स्टैंडर्ड रेशियो. सो मोटर का जो स्पीड है उससे हम स्पीड रिडक्शन करके एजिटेटर को देते हैं. सो एजिटेटर विल बी रोटेटिंग एट 90 आरपीएम, whereas your motor will be rotating at 15 multiplied by 90, right? So it will be rotating at somewhere 1400 rpm. सेकंड थिंग इज, आपने हमेशा देखा होगा कि मोटर्स जो रहती है उसके आरपीएम कितने रहते हैं? 1400, 2900 ऐसे रहते हैं. आपको कभी 200 आरपीएम वाला मोटर नहीं मिलेगा, बिकॉज मोटर्स आर ऑलवेज 2 पोल मोटर्स, 3 पोल मोटर्स. तो बेस्ड ऑन उसका जो कॉइल रहता है ना, सो मोटर आरपीएम आर ऑलवेज इन द मल्टीपल्स ऑफ 700, 700 आरपीएम, देन 1400 आरपीएम, 2800 आरपीएम, right? So because of that we need a gear drive to gear down the rpm. Is it clear, Devan?
Yes, sir. Yes. और अगर डीप पाइप रखेंगे तो रिएक्टर में तो it will not direct come in contact with vacuum. Suppose we are providing vacuum inside the reactor, then if we providing deep pipe, then I think indirect contact between vacuum and reactors inside.
नहीं मतलब मैं क्वेश्चन नहीं समझा आपका.
As per my knowledge, providing a deep pipe for raw material charging, then if there is a vacuum inside the reactor, then वो मटेरियल को टफ नहीं होने
बट आपका
देगा.
जो
अगर
डिप
डीप
पाइप
पाइप
रहता है
होगा
ना,
तो
जो आप डिप पाइप जो रहता है ना उसमें एंटी साइफन होल भी होंगे आपके. इन द डिप पाइप ऑन द टॉप देयर आर सम होल्स. आप देखना उसमें छोटे छोटे 3-3 mm के 2-2 mm के होल्स होंगे, सो दैट आर द एंटी साइफन होल्स, तो उसमें वैक्यूम नहीं आएगा.
so to prevent the contact with vacuum, that's also one of the purpose for providing the deep pipe inside the reactor
नहीं एक्चुअली
to
लाइक
prevent
सी,
from sucking.
यस बेसिकली आपके जो एंटी साइफन होल कैसा है, व्हेनेवर यू आर चार्जिंग द रॉ मटेरियल, राइट? तो पाइप के अंदर मटेरियल जैसे वो डाउन आएगा, इट विल क्रिएट सम वैक्यूम ना, दैट्स व्हाई एंटी साइफन इज क्रिएटेड. अभी आपका रिएक्टर में वैक्यूम हो या ना हो, डिप पाइप का कुछ लेना देना नहीं है, बिकॉज आफ्टर रॉ मटेरियल चार्जिंग आप उसका आरओवी या वाल्व तो आप क्लोज कर देंगे ना, यू विल क्लोज द वाल्व आफ्टर रॉ मटेरियल चार्जिंग. तो उसके वैक्यूम, रिएक्टर में वैक्यूम से उसका कुछ रिलेशन नहीं है.
Okay,
Okay, so that is basically the transient heating. So this is the time t. So mass of the material, cp of the material, overall heat transfer coefficient, that you will calculate from this particular equation, right? And this u is the utility temperature, supply temperature, ti is the initial temperature of the process mass, and tf is the final temperature of the process mass. From that you can calculate the time, right? Now let us quickly go through the shaft design, even though it's a mechanical part, right? तो based on torque, based on the bending moment, right? उसका कितना आप उसको bending moment दे सकते हो और critical speed, ये तीन चीज पे shaft design होता है, right? अगर आपके shaft पे वजन बढ़ जाएगा, right? Sometimes even if you operate your shaft no load condition में, right? No load condition में क्या होता है? Load तो minimum है, लेकिन उसके पास like in no load, like it will imbalance will be created, right? Because of that कम load पे भी वो damage हो सकता है, right? So to there is some critical speed, so minimum speed और maximum speed के बीच में ऑपरेट करना है, right? So higher and lower operating limit के बीच में ही उसको ईजीटर को ऑपरेट करना है. अगर आपने ज्यादा स्पीड पे घुमाया तो भी आपका शाफ्ट डैमेज होगा, कम स्पीड पे भी वो डैमेज हो सकता है, right? So these are the three different criteria for shaft design. So like your basically your power of the shaft will be the total power, that is calculated power जो आपका आ रहा है, multiply by 1.1 because of the transmission losses and 1.2 because of the fitting losses, right? Different fittings on the shafts, right? So आपको basically torque से आप क्या करना है, you have to calculate the torque based on this equation from the power, right? Based on the RPM. Once you get the torque, you have to find the bending moment, right? This is the bending moment 1.5 say 2.5 times of the torque, right? You have to fire this shear stress, right? And this is the basically the ZP factor, right? From that you can calculate the bending maximum bending moment, right? And these are the mechanical equations used basically, right? So we will not care much about that, just I have included. Similarly, with respect to critical speed, right? The range of speed is 70% से 130% of the critical speed should be avoided. So suppose आपका 30 like RPM is 100, so you should not go below 70 and above 130, right? So again, these are the equations for the critical speed. This one is delta factor you will find out, and from that you can find out the critical speed, right? So I will share one Excel sheet, right? I will present, so these things will be clear. Similarly, the hub and key, right? So these are the equations for the hub and key, right? From mechanical point of view, it is important. Just we'll skip this. Okay. So let us see how the scale up is done. So what are the different factors of scale up of the reactor, right? Or the agitator, right? So one is the geometric scale up. So what you can do is जो आपका laboratory में जो था, right? This is a laboratory agitator. Exactly you scale up to the plant scale. But however, this is not possible, right? So what will happen in this case? It will be a total mess, right? It is you should never use this geometric scale up. It can be limited from lab to pilot तक चलेगा, लेकिन commercial scale पे it is very risky, right? You should not do this type of study, right? So suppose just make एक example देता हूँ, right? Whenever you are rotating, suppose there is a lab scale, आपका round bottom flask में एक agitator है, right? Magnetic stirrer is there or a small agitator is there. What will happen? जब वो एक टर्न घूमता है, when it rotates one round, right? So what is the periphery? आपका पेरीमीटर कितना होगा? One rotation यानी कि it will be 2 pi r, that is the circumference. So suppose उसने एक सेकंड में एक रोटेशन घुमा, so it is 2 pi r, that is the distance per unit second. So that is the velocity. So 2 pi r per unit time, that is the tip speed of that particular agitator in laboratory. लेकिन अगर मैं वही एजिटेटर को ज्योमेट्रिक स्केल अप करके उसको कमर्शियल स्केल में भी वन रोटेशन इन वन सेकंड घुमाऊंगा तो वो कितना होगा? नाउ हियर इन माय केस एट द कमर्शियल लेवल your diameter will be very high, radius will be very high, so 2 pi r per unit time 1 second, that tip speed will be very very high. So जो लैब में आप अगर उसको 60 rotations per minute घुमाते हो, so it does not mean कि उसको commercially भी 60 rotations per minute घुमाना है, right? So that's why the fundamental came is geometric scale up हम use नहीं करते, that's why we either use constant power by volume ratio or constant tip speed, right? So we'll see this. So when we talk about the constant power by unit volume, so what we do is from the all the parameters, right? We calculate the power number at the lab scale. So we have laboratory में कितना power जा रहा है, what is the RPM, what is the diameter of the agitator, density, सारे से we will calculate the power number at the lab scale. Now we select the agitator at the commercial scale. Suppose मैंने 6 pbt use किया, sorry 4 pbt use किया या 6 turbine blade use किया, Ruston turbine. So I have the standard power number. I will match that power number with respect to lab and check. So what will be my power at the commercial scale, that will be finalized, right? So you can see here, this is the power number, and volume of the tank is pi by 4 d square h, right? D is the tank diameter. Now power by volume ratio, right? If I do P by V, so it will be power number divided by the volume. Suppose dt by dA, that is phi 1, and h by dt is phi 2. So tank diameter by agitator diameter is phi 1, and height of the agitator to diameter of the tank is phi 2. So dt is equal to phi 1 into dA, and h is equal to phi 2 into dt. So h will be basically phi 2, और dt क्या है आपका phi 1 into dA. So h will be phi 2 phi 1 dA. Substituting this, you will get this particular equation, right? So when you simplify, you will get this equation where your P by V is equal to आपका पावर नंबर है, रो है, n क्यूब है, dA स्क्वायर है. जहां पे रो इज कांस्टेंट, डेंसिटी इज कांस्टेंट, पावर नंबर इज आल्सो कांस्टेंट, राइट? बिकॉज यू आर यूजिंग द कांस्टेंट पावर नंबर थियरी, यू आर डिजाइनिंग एज पर द कांस्टेंट पावर नंबर. सो आपका पावर नंबर भी कांस्टेंट है, योर फाई इज कांस्टेंट, फाई 1 फाई 2. So you are getting a correlation is P by V is equal to K, it is a constant, n cube dA square. So when you do the lab and plant comparison, so what will happen? You will get this correlation. So n lab upon n plant will be diameter of plant, diameter of agitator of plant divided by diameter of agitator of lab raised to 2 by 3. So 2 by 3 is the scale up ratio. So whenever you want to scale up, so you have to use this particular equation, correct? So with respect to different types of operations, blending, mixing, right, suspension, so you have the constant, like different parameters are available, power number by volume ratios, right? So you can refer this. Similar tip speed is also given. So from that you can decide, based on the operation, you can select the power by volume ratio as well as the tip speed, right? So this is again based on the different operations, this power by volume ratio is given, right? So generally we always consider 2 से 3 के बीच में हम consider करते हैं. 2.5 is the ideal choice, right? Similarly when we talk about the tip speed, right? So tip speed is for the low agitation, medium agitation, high agitation, these are the different tip speeds. So tip speed का जो मैंने बात किया, so mostly always we are designing as per the tip speed only, most of the agitators, because when your one rotation at the plant scale or lab scale is not same as that of one rotation of agitator at commercial scale, because tip speed will be varying. So वही है कि आपका laboratory scale में if you are rotating 1 rpm, right, sorry, one rotation in 1 second, it does not mean you will be able to rotate the bigger agitator at the commercial scale at 1 rotation per second, right? So that's why the concept of tip speed came. So with respect to different types of agitators, different tip speeds are available. So you can refer this particular table, right, for designing. Similarly, constant blend time. So this is with respect to liquid mixing and basically miscible liquids, right? So constant blend time with 5% variance. So based on the constant blend time, so आपका blend time lab में कितना आया है, उस हिसाब से you can calculate the agitator diameter at the commercial level, right? So vessel diameter, you know, you have to calculate the agitator diameter. So you know the power number, RPM, everything. If you want to keep the RPM same, then in that case, blend time is constant blend time is also used, right? So scale up factor. So basically when we talk, right, so this was the equation that came, right? ndx is equal to constant, right? So जैसे हमने पावर नंबर के लिए किया, so n lab into da lab, right? da lab raised to 2 by 3 is equal to constant. So n d raised to 2 by 3 is equal to constant. So power by volume ratio अगर constant है तो आपका what is the factor of scale up? This is 2 by 3. So this is the only table which is most useful, highly useful for scale up of agitator. So आपका x का value, so if it is constant tip speed, your x is equal to 1. If it is constant p by v ratio, then your x is equal to 0.67. So आपको ये हमेशा maintain करना है, right? So lab scale versus commercial scale, n d raised to x. So this is the ratios, right, for different scale up factors. So mostly tip speed and power by volume ratio is the common one, right? So you can refer this. So with this, I think we have completed the basically the design and scale up of the agitator. So किसी को कुछ doubt है तो they can share, otherwise I will share one Excel sheet for the calculation. Yes, any questions, anyone?
Uh, yes, I have one question. Sometimes what happens is if we go for the approach of constant tip speed from lab to your plant, because in almost
Yes,
all cases in plant we do the rating work, we don't do the designing part. So,
correct.
so what is the approach there? If there is a limitation in terms of power per unit volume, you are not getting the same power per unit volume, but you are getting a higher tip speed. So, can we
Yes.
interchange that?
See, basically, when you are designing a new plant and you know that that particular agitator will be used for lifetime for that particular operation, then tip speed
No,
is
no.
good
I'm
as tip.
talking in terms of a multi-product plant. I'm talking in terms of rating.
So
Design
your
part is
question is
clear.
like initially like same reactor you want to use. So in that case,
Yes,
P by V will keep on changing, correct?
yes,
Because your motor is
yes,
fixed. You cannot
yes,
change the motor every time. Suppose आज viscous
yes.
माल है, viscous material है, कल नहीं है, so you cannot change the motor. So you are left with only one option, that is a constant tip speed then, right?
Okay.
You see what you do is when your mass is viscous, right? What you can do is if you want to improve the agitation, there are two principles. Either you increase the RPM or you increase the basically this you can say uh,
Agitator sweep there.
so you cannot basically change the agitated dia. So what you can do is you can do with like scale up with respect to tip speed. So suppose आपका जैसे
Okay.
viscous material है, right? So you cannot change the agitator, you cannot change the motor. So what you can change is your RPM. So उसमें भी limit रहेगा. Suppose you are working in MPP plant, right? So initially some reactor was used for liquid mixing, right? Low viscosity. Suddenly now high viscosity liquid में उसको mix करना है, तो same reactor cannot be used क्योंकि मोटर का भी एक लिमिटेशन होगा, राइट? इवन इफ
Correct.
यू रोटेट, सो उसमें आपको फिर टाइम के साथ कॉम्प्रोमाइज करना है. योर बैच साइकिल टाइम
Okay.
विल फॉर द मिक्सिंग विल इंक्रीज. जो
Okay.
लो विस्कस फ्लूइड के लिए 1 घंटे में होता था, फॉर हाई विस्कस फ्लूइड इट माइट टेक 10 hours एट फुल लोड ऑफ एजिटेटर.
Okay. Correct. Okay. Thanks.
ओके.
Sir,
यस.
Sir,
if we
sir,
are
I want to add something.
using variable
Sir, मुझे
frequency
लगता
drive
है
in case of
यस.
agitation motor, then we can
यस.
also maintain the P by V value constant.
सी बेसिकली पी बाई वी एक लिमिटेशन तक आप डेफिनेटली मेंटेन कर सकते हो, कोई इश्यू नहीं है. But when there is drastic change in density and viscosity, then P by V को भी maintain करना it is difficult. So just for your information, all the agitators in industry are like, as far as my knowledge is concerned, are already VFD होते हैं वो. Never they are used for fixed any particular RPM. They are always VFD. लेकिन VFD में भी कुछ लिमिटेशन रहेगा उसका. सडनली लाइक जिसका कैपेसिटी कुछ पर्टिकुलर लोड हैंडल करने का उसके लिमिट से बाहर जाएगा, देन इन दैट केस पी बाई वी वैल्यू हो या टिप स्पीड हो, इट विल नॉट वर्क. सो जनरली हम क्या करते
Yes.
हैं, स्टैंडर्ड इंडस्ट्री में ऐसा है कि वी हैव डिफरेंट डिफरेंट टाइप्स ऑफ वेजिएटर. सो मोस्टली तो पीबीटी ही रहता है. सपोज पर्टिकुलरली कोई इंडिया की इंडस्ट्री है, इट इज ऑल्सो इनटू लो विस्कोसिटी फ्लूइड्स के साथ भी डील करती है और उसके पास कुछ हाई विस्कोसिटी वाले मटेरियल भी है, तो उसके वो दो रिएक्टर साइड में स्पेशली रखता है. सो जैसे स्लरी मटेरियल आता है, जैसे कि इन्होंने बताया एमपीपी प्लांट है, तो स्लरी मटेरियल उस पर्टिकुलर रिएक्टर में डालेंगे, लो विस्कोसिटी वाले मटेरियल इस रिएक्टर में डालेंगे. सो यू कैन यूटिलाइज, आप उस एमपीपी प्लांट में हाई विस्कोसिटी, मीडियम विस्कोसिटी और लो विस्कोसिटी तीनों के लिए डेडिकेटेड रिएक्टर्स आप ले सकते हो. यू कैन यूटिलाइज वेर एवर यू वांट, राइट?
Okay, reactor को categorize करना पड़ेगा product के
Yes,
हिसाब से.
that you can do it, right?
Okay, okay, got it, sir.
So this one is one of the Excel, right? So where your diameter is there of the agitator, right? So liquid level is there, right? This one is the laboratory data, right? So this one is the reactor diameter, right? Shaft speed is there, right? Now this one is the volume, right? So इसमें कैसा है? So whenever you are putting this just a minute. So volume is there, density is there, viscosity, everything is there. what is the type of agitator. So you have to select it, right? Based on that, you can based on that I have inserted a function, right? So your power number and pumping number will change. So it is like 1.7 power number and 0.6. So you can see from this table P6, right? It is changed. Similarly, if I put P4, it will be changed, right? Right. So these are the power number for the standard agitators that like basically available in literature. So what is the agitator diameter to tank ratio, right? So जनरली जो हमारा थंब रूल रहता है फॉर पिच ब्लेड 0.3 से 0.5 का 0.4 का. So based on that I have selected. Now what is the scale up ratio? So basically if I am scaling up with respect to shaft speed, तो यहाँ पे आप देख सकते हैं with respect to shaft speed, right? So यहाँ पे different scale up ratios are there. So with respect to shaft speed it is 0. So what will happen? R यानी कि जो आपका रेशियो था ना constant is equal to v2 by v1 raised to 1 by 3, right? So जो मैंने आपको बताया n d raised to x is equal to constant. So that will come into picture. So in that case your scale up ratio will be 2.15. So this d raised to 14 जो आपका ये जो है scale up ratio है आपको कितना करना था? You want to scale up 10 times, right? So आपका 10 times you want to scale up, so your scale up ratio will be d like 10 raised to 1 by 3. So that's why it is 2.15 is your scale up ratio, right? Based on constant shaft speed. So अगर मैं उसको power by volume constant करता हूँ, so my this scale up exponent will be 2.67. So in that case it will change, right? So after that what will happen? Your RPM are changing based on that all your parameters, volume, right? So base is your volume is changing 10 times, you are scaling up diameter, liquid level. So based on that your power by volume constant, right? So you can see here when I have taken constant power by volume ratio, so power by volume ratio at the reactor as well as the commercial scale, it is remaining constant, right? So power भी आपका बढ़ा, साथ साथ ये भी बढ़ा. Similarly, if I put here the constant tip speed, right? So based on that, your factor is 1, right? So in that case, what will happen? Tip speed will be constant, but your power will be changing, right? So आप देख सकते हो कि रोटेशन शाफ्ट का रोटेशन लैब में कितना था 720 था, राइट? कमर्शियल लेवल पे मेरे को कांस्टेंट टिप स्पीड रखता हो तो सिर्फ 334 ही चाहिए. तो लैब में ज्यादा पावर बाय वॉल्यूम रेशियो था कंपेयर्ड टू कमर्शियल स्केल. So this is the beauty of tip speed. So basically mostly reactors tip speed पे डिजाइन होते हैं, right? Is it clear to everyone? Yes or no? Similarly, this is one of the sheet.
Yes.
Batch heating and cooling time. So this is the volume of the reactor, surface area. So wherever you are, suppose you are working in a MPP, right? You know the heat transfer area of the reactor, you know the volume. और अगर कोई बोलता है कि मुझे इस particular reactor में कोई एक reactor mass है, उसको 30 से 80 डिग्री heat करना है. So what will be the time? So you can use this particular Excel sheet or the transient heating or cooling equation once you have the overall heat transfer coefficient. So using this, what you can do is reactor volume, you know, surface area, you know, overall heat transfer coefficient, you know. So based on that, initial temperature is 30, final temperature is 50, specific heat I'll know, density I know. So from that, what I will do, I'm using steam as the heating media, right? So when I'm using steam, 8 kg pressure है तो उसका temperature from the steam table I will get, latent heat I will get, velocity I have considered 20 for the Reynolds number, right? So this equation I will be using mc upon ua ln t1 minus t1 t1 minus t2. So from that equation your time is coming out to be 3171 second, that is 0.88 hour. So अगर उतना मास को मैं हीट कर रहा हूँ तो, but in this case suppose it is a endothermic reaction, आपका रेट ऑफ रिएक्शन होते होते ठंडा भी हो रहा है. So in that case what will happen? So अगर मैंने इतना टाइम लगाया, अगर नॉर्मल सिर्फ मास को 30 से 50 हीट ही करना है विदाउट रिएक्शन, सो दिस इज द टाइम टेकन एंड व्हाट इज द अमाउंट ऑफ हीट सप्लाइड? सो mcp delta t divided by this particular time, right? So mcp delta t divided by this particular time. So I have supplied energy at this rate, so 85301 joules per second, यानी
कि what ये रेट से मैंने सप्लाई किया. Suppose now molecular weight of the reactant is this, number of kilomoles of reactant is this, and heat of reaction is positive, यानी कि endothermic reaction है. So what will happen? मुझे और इतना हीट निकालना पड़ेगा, right? तो मैं ये हीट कैसे निकालूंगा? So what I can do is energy divided by power, so it will give me seconds, right? So इतना हीट निकालना है, लेकिन कितना रेट से? This is my rate. So based on that, this is my time, right? So how it will come? It will be coming like this way. So total time मेरा कितना होगा? एंडोथर्मिक जो था उसका हीट निकालना है प्लस 30 से 50 लेके जाए, तो दोनों का समेशन. सो टोटल my heating time will be 6.3 hours, right? What will be the steam consumption based on the latent heat, and what will be the density of, based on the density of steam, what should be my line size if I have considered 20 velocity, 20 meter per second, right? So basically this is for the reactor heating and cooling, right? Is it clear? Understood everyone? Yes or no?
Yes.
Okay. And next and the last one, this is basically the mechanical design. So there is some equation like problem statement. There is a flat blade turbine with some diameter. Turbine is there, right? Height, viscosity, density, RPM, everything is given, right? With different types of stress, yield stress, shear stress, crushing stress, right? So this is basically the mechanical design. So these are the data that are available, yellow one, right? So power requirement, Reynolds number I know, and power requirement I will be calculating from the power number. This is a correction because of the gland losses, transmission losses. So actual power requirement is 11 HP. Right? So based on that, what is a critical torque, maximum torque, right? Different what are the stresses? From that I will calculate the, from the bending moment or from the critical speed, I will calculate what should be the hub key and your shaft diameter, right? So I think like mostly you should not worry about this. This was the mechanical design. Just I have put here for the information and just for the knowledge how the scale up is done, right? So I think I have delivered good with a short period. I have covered a good amount of topic. So I think that's it from my end. If you have any questions, then I am here to answer. So you can ask.
I have one last question. The PPT was really good. I just wanted to ask one question. In lab, when we go for, we either use a round bottom flask or a conical flask. Okay.
Yes.
So how do we convert the diameter from there to your reactors where we almost have either ellipsoidal or spherical type of bottom and type of design geometry?
We have, I told there might be some geometric correction factor, or generally it is not a good practice to do in lab. So generally, see, two things are there. Some industry do the lab scale and directly based on the lab data. See, some products are there which are like, they are manufactured since long time. So some even don't go for lab also, right? Or the consultants are there. But for a new molecule, after lab, piloting is must. सो फ्रॉम माय ओपिनियन आई विल से लैब के बाद आप पायलटिंग करेंगे तो आपको स्केल अप के लिए डेटा अच्छा मिलेगा. सपोज यू आर स्केलिंग अप, सपोज अ मॉलिक्यूल, अननोन मॉलिक्यूल इज गिवन, आप एक जगह पे लैब से सीधा कमर्शियल जा रहे हो, एक जगह पे आप लैब से पायलट एंड देन यू गो टू कमर्शियल. सो यू कैन फील द डिफरेंस इन दैट सिनेरियो. सो काफी दिक्कत आती है कमिश्निंग में इफ लाइक यू आर नॉट doing the piloting. That's where the importance and the beauty of the pilot studies come into picture. So that's why I suggest कि 100% I agree, your question is valid. RBF में करते हैं और plant में करते हैं, so data में काफी discrepancy रहेगा. You will not get the accurate interpretations of the lab data. That's why the pilot studies are must. Okay, especially for the new molecules, specialty chemicals. Okay. Any other questions? Anyone?
Yes. If we perform same geometry at lab or plant, how I can consider a factor for with baffle or without baffle? We don't have baffle at the lab scale.
Correct. सो बेसिकली वही मैं बता रहा हूँ, लाइक लैब स्केल में आपके पास बीकर होगा, राइट? सो बीकर में सिमिलरली जैसे आप बैफल की बात कर रहे हैं, तो अब हीट ट्रांसफर भी कैसे करते हो आप लैब स्केल में? तो यू यूज आइस से करते हो या आप बाथ में, हॉट बाथ में रखते हो. सो उस केस में आप कैसे जस्टिफाई करेंगे? बिकॉज ग्लास में होता है, राइट. तो ग्लास इज नॉट अ गुड कंडक्टर, लेकिन शायद हो सकता है कि प्लांट में एसएस के रिएक्टर में हो, राइट. सो इन दैट केस लेबोरेटरी से सिर्फ आपको इंटरप्रिटेशन मिल सकता है, जहाँ पे आपका प्रोडक्ट है सिंगल या 2 स्टेप्स में हो रहा है, जहाँ पे सिर्फ ब्लेंडिंग और मिक्सिंग ही है. सो इन दैट केस इट इज ओके.
ओके.
इज इम्पोर्टेंट. सो उन केस में इट इज डेफिनेटली लाइक आपको लैब के बाद पायलट स्टडी करना जरूरी है. सो आपको स्केल अप के लिए सारा डेटा मिलेगा, अदरवाइज यू विल बी ब्लैंक, आपके पास कुछ डेटा ही नहीं होगा स्केल अप करने के लिए. लेकिन जहाँ पे आपका सपोज यू आर ऑलरेडी मैन्युफैक्चरिंग, सपोज आपका एक साइट है, वहां पे आप ऑलरेडी एक प्रोडक्ट 10 साल से बना रहे हो, उसका आप दूसरा प्लांट डालना है, राइट. यू वांट टू एक्सपांड द प्लांट, कैपेसिटी बढ़ाना है, तो उस केस में आप डायरेक्टली लैब के बाद कमर्शियल में जा सकते हो, क्योंकि आपको छोटा मोटा इंप्रूवमेंट करना है, आपको मालूम है कि पुराने प्लांट में क्या प्रॉब्लम आ रही है, मुझे कहाँ चेंज करना है. सो एग्जिस्टिंग प्रोडक्ट, एग्जिस्टिंग मॉलिक्यूल के लिए आप पायलट ना करें तो चले, लेकिन हर एक नए मॉलिक्यूल के लिए इट इज like mandatory, or I can say it is good engineering practice to do a pilot study and then go for commercial.
Okay, I have another one question, sir.
Yes.
We have lab scale gas induction autoclave. Then
Correct.
how I can scale up the gas induction rate?
Gas induction rate.
Yes.
So basically here your you are using the gas induction turbine, so scale up with respect to that will come into picture, where like there are some standard literatures. Second thing here, what is your like laboratory में आप जब करते हो, right, whenever you are monitoring, so what is the droplets or you can say bubble का size कितना है when you are doing the induction, like autoclave hydrogenation होगा, so whatever the bubbles है उसका size कितना है, what is the dispersion rate उसका, like it will keep on rising, वो ऊपर जाएंगे नीचे आएंगे, so what is the residence time distribution, उसका drag and buoyancy क्या रहेगा, right. so एक हर एक का जो आप करेंगे ना, so like माइक्रो लेवल पे वो पिक्चर में आएगा. अदरवाइज सेकंडली व्हेन वी सी ना, so उसमें आपका इंपॉर्टेंट यही है कि उसका जो गैस इंडक्शन टर्बाइन है विद रिस्पेक्ट टू ज्योमेट्री. सो दो चीज है, व्हेन यू गो टू एक्चुअल स्टडी, सो वहां पे आपका ड्रैग है, buoyancy है, दिस विल कम इनटू पिक्चर, डिस्पर्जन, like bubble size, everything, right. But when we talk about the direct scale up, तो आपके पास गैस इंडक्शन टर्बाइन का डेटा है कि how to scale up from like a lab to pilot, sorry, lab to commercial, so you can directly use that data. And second thing, आपके पास like कुछ vendors available होंगे, so based on that particular gas dispersion rate, they can suggest you the type of vegetator.
हेलो सर.
Yes.
हाँ सर, एक क्वेश्चन था. जो कंपनी में रिएक्टर होते हैं उसमें जो प्रेशर का यूनिट mmHg और mmH2 होता है, तो फिर वो दोनों यूनिट ऐसे अलग अलग क्यों और कब यूज करते?
See, basically it is like suppose आपको आपका वेट करना है, whenever you want to weight yourself, आप कौन सा यूनिट यूज करते हो, केजी, करेक्ट. लेकिन आपको अगर कोई टैंकर है या कंटेनर का वेट करना है, यू यूज टन्स. But when you go for buying gold, you will not use kg or you will not use ton, you will use grams or milligrams, right.
Yes.
So basically उसका purpose is आपका suitability कहाँ पर है. So if it is like autoclave, तो आप उसको बार एटमोस्फेयर kg में बोलेंगे, right. If it is vacuum then mmHg. अगर आपको सिर्फ ब्लैंकेटिंग पर्पस यूज करना है then it will be mm of water column, right. So जितना आपका कम प्रेशर है उतना आपका यूनिट छोटा होगा, जितना आपका ज्यादा प्रेशर, ऑटोक्लेव में 200 एटमॉस्फेरिक पे प्रेशर पे रिएक्शन होता है, सो वहां पे आप एमएम वाटर कॉलम में करने जाओगे, आप 2 करोड़ 5 करोड़ एमएम वाटर कॉलम नहीं बोल सकते. तो दैट इज द रीजन, सुटेबिलिटी का इशू है. तो बेसिकली गैस इंडक्शन टर्बाइन में यू हैव टू कंडक्ट द डिस्पर्जन स्टडीज, राइट. मोस्टली वी डू दिस पल्स ट्रेसर experiment as well as the residence time distribution, so their segregation model will come into picture. So here this is the best example, gas induction turbine, it is a best example for like reaction engineering, जो हमारे academics में जो पढ़ते हैं उसका scale up का it is one of the finest example. So you can study that. Second thing is you can also use the data which are available for scale up related, जो मैंने graphs दिखाया ना कि how to scale up with respect to power number, gas induction turbines है, so you can use that data directly for scale up of the GIT. Is it clear?
Yes, sir. Yes, sir. Thank you.
Any other questions? Anyone?
Sir, do you have any conceptual study material for uh, on this topic? Because I'm not able to recall all of it, so that's why I'm asking.
Like what type of material like you are asking about? Like
Uh, anything just to refresh all the thing that I've done during my academics.
yes, Rega, we have all like mostly we have the academics also, not an issue, but we have all the study material and design related things which are applicable at the industrial level. So mostly we are into process design, what is happening at the industrial level, right? Academics is no doubt it is happening, right? It is useful. Raoult's law that we studied, we are applying, but up to what extent the like जैसे कि reaction engine की बात करें, so what up to what extent we are using, so that is not happening at the commercial level or in the professional life. So mostly we are into training with respect to the troubleshooting and design of the equipments which we didn't study during the academics, right? So definitely अगर कुछ रहेगा तो we'll definitely provide you, not an issue. You can just mention in the this chat box or during the feedback form, so we'll help you out.
Okay, thank you.
Oh, so please send the material, sir. So we'll see about it and
Sure,
get
sure,
some knowledge of it.
definitely.
Thank you, sir.
Okay, so just from my end, I will say it was a very good, wonderful session to interact with all the students, right? So happy to interact with you all. And just I will say this type of interactive sessions among our chemical engineering professionals will help us to grow as a group, as a community, and we can also have this type of discussion so that we can improve our domain knowledge. And we are into this type of studying, like this was one of the topic for the process design engineering.
Please
Similarly we have
share.
sorry, yes, so we are also conducting classes for Aspen HYSYS, Aspen Plus, FlareNet, HDRI, process engineering, distillation column troubleshooting. So interested student can register. Out of which process design engineering we are having the entire course where we'll be teaching the design of the all the types of equipments starting from the design basis to mass balance, energy balance, pump, reactors, exchangers, agitators, columns, fans, blowers, right? So control valves, instruments, everything is covered. So it is a detailed 2 month course. So that's it from my end. Handing over to
When,
the team. Yes,
when will be the next class, sir?
सर कोई बुक आप रेफर करना चाहेंगे इसके रिगार्डिंग प्रोसेस इंजीनियरिंग के रिगार्डिंग जिससे वी कैन
okay, you
हैव
can
मोर
use
नॉलेज अबाउट इट
Stanley and Wallace. You can use Ludwig. You can use Richardson and Coulson. I will suggest for equipment designing. Right. Other than that, like different equipments have different categories. Right. So pumps के लिए Larry Butches is there for this fluid flow. You have some different books. Right. But mostly you can use rule of thumb. That is a good book. Rule of thumb is there बेसिकली फॉर केमिकल इंजीनियर. सो सारे थंब रूल्स गाइडलाइंस आ जाती है जहाँ पे आपको सारे कैलकुलेशंस नहीं करने पड़ते हैं, राइट?
ओके सर थैंक यू सर
When will be the next class, sir?
Even I don't know when the team will ask then.
Okay, sir. Okay. Thank
Okay,
you.
so
So we can
that's
expect
it from
monthly
my
one class
end.
will be there, huh?
Yes,
We can expect to have monthly one class will be there.
yes, maybe yes. Okay, so
Okay, sir.
that's it from my end.
Thank you very much.
So Komal, you can uh, take over. You can just brief about the courses and we can end. Yes.
Thank you, sir.
Okay, so that's it. Thank you everyone for joining.
Thank you, sir.
Thank you.
Thank you, sir.
Just a minute, sir.
Yes. Hello. So anyone have any kind of doubts related to trainings and other kind of webinars?
Hello everyone. I hope everyone liked the session and everyone gained some kind of informative knowledge from this reactor and agitator designing session. Okay, so if anyone have any kind of doubt related to trainings and other kind of things, you can just ask, or you can put any kind of doubts in chat box itself. Okay. Else you can also connect with our Came Club team. Okay, you can visit website www.cameclub.com for any other information, or you can just drop mail on info@cameclub.com. Okay, so thank you for your cooperation. We fine, Vaibhav, we can wind up the session. Okay, we are going to wind. Thank you everyone. Bye. Good night. Okay, bye everyone. Good night. Take care.